First speaker of this session is Martin Mundt, and he's going to talk about memory. He's an independent research group leader at TU Darmstadt and SCM.ai, where he leads the Open World Lifelong Learning Lab. It's a great name. It's OWL.
OWL. It's covered.
He's also a board member at the nonprofit Continual AI and a core organizer of Cure AI. Was the Diversity and Inclusion Chair at AAAI 24, and currently serving as a review process chair for COLA 2024. So thanks a lot for all the service work that you do.
That's enough.
Previously, he was an interim professor. Should I continue?
I think it's fine. It's enough. Don't do all the previously stuff.
Yeah, he's done a lot of things previously, and yeah, he's going to talk about continual learning. Thank you.
Thank you, MT. So I did a provocative title, maybe. It's like challenging in the title. Challenging memory is a solution to continual learning. I think we'll find that there's nothing so provocative in the talk in the end, and just want to capture your attention. But it's basically going to talk about memory in the sense of how people usually do it and when it's useful, maybe when it's not so useful. And so the majority of you were here on Friday, so I did give a tutorial on continual learning, so I'm really not going to go into all of that stuff again because it's just going to bore people. But if you recall, most people kind of framed this continual learning problem as this idea of you have these chunks of data arriving over time, or maybe you call it experiences, and you assume that there's this one model that you update over time, and you want to basically accumulate all the task knowledge over time and be sure that you can kind of perform on all of them well, right? So there are a couple of assumptions in there, you observe these experiences or data strictly sequentially with no access to prior data or extremely limited access, and you're going to assume that you want to avoid this forgetting thing at all costs and accumulate knowledge, right? So if you remember the tutorial on Friday, again, just going to go through it super quickly, we've seen these kind of curves that we're showing well, if you in fact were to block training and only see task 1 first and then task 2, you'll get these kind of performance curves that are going to perform well on whatever task you're presently seeing, unless you do any of the things we were talking about on Friday. So one of the questions I've been asking myself, and I'm not the only one, there's this paper from Antonio Carta and others from 2021 from which these graphics are taken, is this is nice, but nowadays there also exist really a lot of models that are already trained, that are already pre-trained, they're uploaded everywhere. So why think about just continual learning from data routing over time and not think about data as continual learning as models arriving over time, or continuously merging models into one bigger model. So I'm not really going to talk about model merging today, but I'm going to talk about something maybe similar. And I guess the one thing, this is a nice paper, but the one thing they're assuming is they're going to say they're going to take pre-trained models, but what they're going to do is they're going to still evaluate them and train them on a lot of data. They're just going to use some natural proxy data from some out-of-distribution thing. So in a sense, it's assuming no access to prior data, but it's assuming to some access to related data in the present, which is well, you can decide yourself what you think of that. But I really want to think can we do this thing on the right without access to prior data? So we know what the model is trained for, but we don't know sort of what the data is it was trained on. So in this talk, basically, this is the thing I'll talk about the majority of the time, and then at the end I'll give you another example. So with this big question of essentially 2 examples to question the role of data memory, but question here really means when do you really need memory in the sense of storing data, and when is it sometimes hurtful?
Can I? Sorry,
yeah.
Sorry, you know that I will do this.
No, actually, this talk is decently short. It's going to be 40 minutes, so there's a lot of time for questions.
Great. So memory is usually about the past, right? So but you still use the word memory, even though I think you're referring to something that is collected irrespective of the past, or is it the same memory?
It is in the past in the sense of the data that has been used for training a model, and then that model is it's somewhere, right? So it's in the past because it's been used for training.
So it's the training data from the past?
Yes.
Okay.
The data you'll see in a second. The data A model was trained on, basically, right?
Okay.
So the specific paper, like I said, I'm going to talk about for the majority of this talk is really like a student's Stephen Brown's paper, which we presented at AI Stats this year. And it's called Deep Classifier Mimicry Without Data Access. And so the summary of this paper is really, it's going to be, can you distill like the knowledge in quotation of a classifier without knowing what data was trained on, like data free, and without sort of doing a lot of assumptions on like what specific kind of model it is. And then just for the second point, because I said like when can memory hurt, I'm gonna sketch continual confounding for you as a thing where maybe memory can hurt, which is something though that Roshni is gonna present in her poster later today, I think, so I'll really just sketch it. So let's get into this, right? So the question basically is, can we mimic models without access to training data? So you have a model that's uploaded, and you want to now train a second model that just basically is the same thing, but you want to extract the knowledge, but you don't have access to any of the training data because that's not usually what people upload. So the popular thing that people use when people talk about knowledge distillation, at least in neural networks, is, well, this technique called knowledge distillation that I think Hinton, Vinales, and Dean proposed in 2014. And what they basically say is the following. So you can think of models in different ways, like the parameters and the data was trained on, but you can also just think about input-output relationships. So in the specific version of a classifier, you can take some sort of teacher or like some pre-trained model. It's trained on something, and you can try to make a student mimic this by trying to preserve the input-output relationships. So what that means is, if you think about loss functions, is there's a certain part of the loss function like this bluish part on the left that's going to be like something like a cross-entropy loss, and is usually trained to match the labels of like your classification data. And in addition to this, what you could do in knowledge distillation, rather than matching this blue part, which is what you do in like standard training, what you could do is you could make the student try to predict the exact same thing the teacher is predicting for the data, right? So the teacher is not going to spit out like 0, 1, 0, 0, 0 for a classification vector. It's going to spit out some like continuous values, and you're trying to essentially make the student regress that, if you so will, right? And so in the sort of case of knowledge distillation where you don't want to match the actual true labels, you'll just do the green part alone. You'll just try to make the student predict the exact same the teacher is doing. The question, of course, is how can we do this without knowing what data the teacher was trained on and not having access to it, right? So this assumes that you can actually pipe in the original training data, query what the teacher is putting out, and then learn the student to mimic that. And so we tried a couple of different things that I just want to show you what like maybe current pitfalls are or caveats that you could fall into if you try just like data-free knowledge distillation in naive ways before sketching the kind of solution we came up with. So consider a fairly easy 2D example. Maybe we can turn off this light here. I think it's a bit, yeah, there's going to be a lot of color, so I think thank you so much. This is just like a easy 2D classification example before I show you some like higher dimensional stuff, right? So this is 2 Mundt's data set. You probably all know it. And you can train a neural network on this, and you can get like a decision boundary on this teacher. So you have these dots that are of 2 different classes, right? And then you can visualize the class prediction where the green part is like very confident on one part, the purple part is very confident on the other class, and then light in between is basically the part where there's the decision boundary, right? And so what are the things you could do if you wanted to train a model to basically predict the same thing without knowing all these circles? So first thing you could do is you could try Deep Dream, which is, I mean, it has a fancy name, but it's really something very easy. It's essentially just saying, sample some noise, and now set a class label, and do a gradient descent thing to maximize the class label for by sort of modifying the input. Rather to keep the parameters fixed, you just modify the input to maximize. And then you can put some like prior on this, like if you're working maybe not here, but if you were to work in image space, you could do the total variation thing that Thomas was, for instance, talking about in his tutorial on top. Now, you do this in this example, you'll create some data, like some synthetic data, and it's going to look like these triangles in that box that says naive on the top. And so these are nice examples in the sense of that they belong to the correct classes. The only issue though is now, if you were to take this, and if you were to train a student from scratch on this kind of data, what it would actually learn is like just a linear separation because, well, it's kind of spread out, right? It's very far out, so you'll just get a linear line here. And if you plug the original test data into this, you'll naturally see it's kind of obvious that this is not actually doing the same thing as the original teacher does, right? So, okay, so what's the problem here? The problem here is that, in a sense, of course, the synthetic data doesn't follow the original data distribution in some way, we've never made it to, but it's also like too far away in a sense that like you're just saying maximum confidence, so it can be anywhere way far away from the decision boundary. So what is a different thing we could do? We could say, well, let's use a generative model. Let's maybe not sort of predict just highest confidence. Let's do some, this is a GAN actually, let's do some generative adversarial network. Let's do like a fooling kind of game and try to make that, create synthetic data to generate stuff that would actually satisfy sort of the teacher in a sense. And the thing that then happens is you can generate some data. You can see it in these triangles over there. And they're quite nice in the sense of that they're close to the decision boundary of the teacher. You can see it in these in this zoomed in panel. Maybe it's too small for you, but it's sort of very close. However, there's the caveat, of course, that like it doesn't actually capture the region. It's just gonna give you like a very local kind of part of the space because there's nothing you have put in to sort of spread. So if you again train a student model on this, you'll get a linear kind of separation because it's very local, and then you'll kind of get a similar pattern again, right? So the question is, what can we do to avoid this? And what can we do so that basically we don't synthesize data with generative models that collapse? So what is missing, right? On the one hand side, you can think of this kind of what we call naive here, like this deep dream kind of idea. It's problematic because the classes aren't close to the decision boundary. In the generative case, or at least the naive version that we tried, and you might want to do 10,000 tricks to alleviate this, but in the naive sort of application of a generative model to this scenario, you're missing the part where you disperse samples along the boundary. So what we're proposing is a nice acronym that spells out CAKE. It's called contrastive abductive knowledge extraction. So contrastive you'll see in a second. Knowledge extraction, well, because you're trying to extract the knowledge. And abductive really because we're saying, well, if you want to mimic the classifier, actually the only thing that matters is the decision boundary. You don't care about capturing the original training distribution. If you manage to create samples along the decision boundary and you capture the decision boundary, like that's the knowledge of the classifier. So the main idea is basically coming from, well, it's not coming from there, but I hope the thing just motivated it for you, that what we're going to do is we're going to do three things. We're going to sample pairs, and we're going to contrast them, and we're going to do so noisily to basically capture the decision boundary of the teacher with some regularization on top. So how does it work? So the first thing is, if you want examples to be close to your decision boundary, and let's stick to the binary case just for simplicity, right? Like binary classification, 2D kind of stuff, just for simplicity. Don't sample like one synthetic data point or one noisy example, sample two, give them two different labels, and make sure their label is maximized, but also make sure that they stay as close to each other as possible.
So sample two, if you say they have to be different, you only sample one.
You could also, we tried both actually, you're right. So you're saying like, why would you sample two, you could only sample one?
No, but you say you sample two, but you say they have to be different. So then you actually sample just one.
I'm not sure I got that part.
Okay. to get it.
Yeah. It's fine, or, sorry, like,
No.
or the mic is not working, is that the problem?
It's more, you said you sample, but you sample in pairs. But then you say that they have to be different. So then you sample just one and you flip the other one. So the other one is not a sample. Only the first.
Okay, maybe my use of the terminology sample is very loose here. I think what I mean is you like create.
It's a bit creative.
It's like, yeah, maybe I should be careful with the wording. I think like we create two random noise vectors.
Oh, yeah.
With two different, like, yeah, maybe.
Two in a singular space, you know. But only one has the correct distribution. This is what
You're doing what he's saying. So,
there are lots of nuances to this actually. Like, so we did try a bunch of things. Like, you could actually, what you could also do is you could like just take one sample, like basically duplicate it, set two different labels, and then start dispersing. Like, so it's same start point. Like, it'll all work for the purposes of the empirical part in this. Yeah. So the essence, however, is like you want two noise points basically, and while you kind of start then maximizing the label part, you want them to stay close so that basically they'll have to be at the point where the decision boundary, like it flips, right? Like it flips from one label to another. That's the contrast part, so you stay close to the decision boundary. And now the other part, and this is because what we've seen is we have the issue that we don't want to capture like any point and just collapse like some part of the decision boundary. We want to basically span this. So there are two ways in which you could do this. They're both in the paper. They actually both work. The thing we first came up with is we said, do a diffusion process kind of thing, right? So specifically here it's Langevin dynamics. So what you do is you basically, as you update the X, you have this like explicit noise process on top, right? So you inject noise. You can see it in the second and the third term on the sample that makes sure that like it actually disperses. After we've done this, someone said like, well, but there's so many sources of noise. Can't you just do like some really ad hoc things, like stochastic gradient descent kind of stuff, and just do like some sort of do learning rate things and so on? And so we tried, and this does fairly well too. So if you're not fond of diffusion kind of stuff, you want to do some hacky ad hoc implicit stuff, it's also going to give you the same thing. And the third thing is kind of an optional thing. It's you may not know what the model was trained on exactly, but you know what the model was trained for, right? So if you know this is an image classification model, for instance, you could totally do this total variation prior that's kind of set here, where you just say that in your synthetic example, like when you start updating it, you want adjacent pixels to kind of be similar, right? Because it's an image, most images are natural, they won't just have like very adversarial kind of noise patterns. But this is more like an optional thing to do, and you can use other sort of knowledge that you have about the type of data that you can plug in here. Yeah, it's like a plot. He was just saying, is the green on top of the blue and orange? Yeah, the green thing is like a bonus thing. Like, usually you have that thing. It gives you something if you add it. It's kind of smart to do. Like, it doesn't make a lot of sense in the 2D example that I've just shown, but if you go to like high-dimensional image stuff or so, it usually gives you some bonus. If you plug that in, it makes the like generation part easier. But you can create totally like adversarial examples I've shown you later that will do the trick. And then I'm just putting this here like, or any other contrasted loss or like any other noise mechanism or any other data prior, because I think those, actually this is not like very exclusive to these particular sort of equations. It's more like, these are the elements that you could think of you need in order to get to this kind of desired goal that we have. So if you do this in this 2D example, you'll actually get the following. So this is what cake does. So you can see that the triangle data that it generates in the second column, it is it's dispersed, right? Not all of it is actually exactly near to the decision boundary because it can disperse like in a different direction depending on how strong you set the diffusion thing. And importantly, it's not actually trying to mimic the original data distribution. I mean, there's no way how to. But if you train a student model on it, you'll get something that performs almost exactly the same as the original teacher does on the test data in the rightmost panel, right? So you get pretty much a very similar decision model when you train the student model. So up to now, I think maybe this is not too impressive because you're not really probably not understanding the implications of like why this is cool. Like the cool part actually lies in the fact that we didn't really put a lot of assumptions on like what kind of model we're using into this process and like what kind of things we do. So there exist a bunch of works in the literature that can achieve very good knowledge distillation without data access, but they'll do like very specific things. So one popular thing is like you take a neural network that has batch layers, you can minimize, like you can create synthetic data examples, minimize DKL divergence to every single like intermediate layer's Gaussian distribution. But this requires you to have a neural network, access every layer. It has to have batch norm, you need to minimize DKL divergence. So it's like doing a lot of assumptions on model type. And if you think about what we do, it doesn't do that. So let me show you like two interesting kind of things you can now do that maybe are not so easy when you're constrained to like knowledge distillation from a particular neural network to a particular neural network. So the first thing is, well, it's a neural network thing I want to show you, and it's, I think this is CFAR classification, and it's doing cake, basically, knowledge distillation across residual neural network. Well, I called it scales here, but basically what we're looking at is, on the x-axis, we have a teacher that has a specific amount of layers. So residual networks you could characterize by like how deep sort of the network is. And on the y-axis, you'll see the student accuracy after it's like taken these synthetic data examples and trained on it. And the student also has different size in terms of depth. So each of these bars, one is the teacher, and then you have like 152, 150, 34, and so on for the student. And so two things you can see. The first one is you're going to lose some performance on this like higher dimensional image case. We think it's actually a decent amount of performance you lose. Like if you compare this to other literature methods that that do put assumptions, they'll also not be extremely great. But then it's actually quite stable across the kind of different student sizes you pick. So you can distill like a 152 layer network in this particular case to even an 18 layer network, up to the point of 4 where maybe the small network's just too small in terms of capacity. And now you could play this along with sort of different teacher depth, smaller teacher, different students, like maybe larger student, smaller student. And as we go, you'll find that as long as I guess you don't do some like obvious things like limit the capacity of the student or the teacher like extremely to like only 4 layers or something, it'll do fairly well. It'll be very consistent. So you can see the error bars are kind of small, like if you keep repeating these processes. And the different bars, they don't differentiate too much from one another. So this is interesting, but maybe what's more interesting is, what if you did this across different types of models, right? So this is something that a lot of knowledge distillation methods that even the ones that do assume data access would have a hard time doing if they optimize like some intermediate layer activations or something. So here's well, our most popular MNIST example that we all love, right? So this is where you get to like 100% test accuracy, or like 99.2 or something. And in the first column you see you have a multi-layer perceptron teacher, and you have different kinds of neural networks here, like a multi-layer perceptron, I think this is LinNet, like a 5-layer convolutional neural network, one of these like 18-layer residual networks, and a visual transformer. And you can see that the MLP, the CNN, the ResNet, they actually perform quite well. The model that matches the teacher model performs the best, but even the ResNet is quite close up, except for the BIT, which actually performs really bad. It's not random chance, like random chance will be 10%, but it's not much better than that. And so we can try to go through the combinations, like what if the teacher is a convolution neural network? You'll find that, again, the convolution neural network does very well. The residual neural network is okay. The MLP starts to be much worse. The visual transformer sucks. Same pattern again, like teacher is now a residual neural network. The less complicated models, they start to be a bit worse. The residual neural network is fine. the visual transformer is bad, up to the point where you take a visual transformer, which actually works well in a visual transformer, but also kind of works well for the ResNet. So the thing, I guess, like this is a hypothesis, like there's no like theoretical evidence for this, but what this looks like to us is you'll be fairly fine if you take a model that's like less complicated, maybe like less inductive bias, like an MLP, and take more complicated models, but not the other way around. So if in doubt, maybe you could say that maybe you could always pick a residual neural network and it's kind of doing okay-ish, like those are not bad. But clearly, like it's kind of hard to take like a multi-layer concept and distill it into a visual transformer, but not the other way around. Yeah, you have a question.
It's very short. Are these all your method?
Yeah, these are all our method. Like these are just sort of intra comparisons, right?
So, so just to be specific, it does look like it matters what the architecture is.
It matters what the combination of the architecture is, right? Like it's less about sort of like each sort of pair of bars, it works. But once the architectures start to be different, it kind of matters like how different they are. Yeah, it's interesting. So we didn't put it in the paper because we ran out of time, but because the only thing you're basically assuming is differentiability, I suppose, right? You can actually do this for like a support vector machine or like a probabilistic circuit. Like we've tried this for probabilistic circuits, and you'll see this even more. Like it's going to be a bit harder to go from a probabilistic circuit into a neural network.
Did you try any convex case?
No. Do you want to try it? I'd be happy to. Right, so this is kind of the thing, right? And then I guess you can look at these like big performance tables if you want to. I mean, there's lots of numbers in there. You'll find that some things are harder than others. I think the TLDR is that ours is like the only method that doesn't put sort of very constrained assumptions on like you need this exact model or you need data set access. That does very well. If you compare it to some of the methods that do in fact use data, like just the knowledge distillation, like on top, you'll get slightly better results than we do. Of course, like you can make the performance on CFAR 10, for instance, ResNet 34 to ResNet 18. In knowledge distillation that uses all the training data, it's like 94.3% accuracy on test. Ours is like 78.9 plus minus a bit. So there is a like decent amount of drop. I'm not going to say this actually matches the performance entirely, but I actually find the performance drop to be a bit surprising given that this is rather high dimensional. It's like images, it has lots of pixels, and you're not really assuming anything on like what the original data is, right? So I personally find this impressive, and you can make your own kind of idea out of it. What I find most interesting, however, though, is the like lack of assumptions that are in this method, right? So I started with this motivation of continual learning, and well, cake is clearly like data free in the sense of like, I mean, data free is a weird word. It's using synthetic data that you make up yourself. It's definitely not using like any real data ever. So you don't need to know what like a thing was trained on. It is model agnostic in like a large amount of assumptions. So sure, it needs to be differentiable, but you can basically pick like any kind of neural network and like similar kind of models, and it'll do the trick. And that allows you to do these distillations across like different scales and model types, and you can play around with it. And I find that quite interesting, right? So maybe for continual learning, where usually you cannot make these assumptions, this will be interesting to try out. So disclaimer, we haven't done this for continual learning yet, but something like this would be very interesting to try. It also doesn't produce data lake samples because there's no reason to. So if you don't put like these data priors or anything that are like extremely heavy on this needs to look exactly like an image, the curves I've just been showing you, the data you generate actually looks like this. So like even the CFAR data, that's kind of, maybe you could see some object or end this, like you're not really seeing anything. So I think this is quite interesting. Yeah, I'll get to you in a second. This is quite interesting because it probably allows you to now also think about not just continual settings, but maybe federated settings where people care about privacy, like maybe this kind of data, I mean, there's more work that needs to be done to actually maybe prove or empirically show that these examples do not in fact recover originals. But under that assumption, at least visually glancing at it, it doesn't look like it, and maybe you could use it in like a privacy preserving kind of setting as well when you communicate. You have a question?
Did you test this across also like different architectures, or is this just one?
Yeah, no, it's across different architectures.
Do you notice anything different?
No, they always look like uninterpretable. So it's quite interesting, I find, right? There's one more thing, and maybe I think I've just realized this. Like, question first, yeah. I mean, we have a lot of time. This is already like 2/3 of the presentation. Yeah, I told you I'm.
So, did you check how much training data you have to create with respect to model hubs?
We did like a very empirical thing. Didn't do anything sort of very sound, I would say. There is, for these data sets I've been showing, we're like starting to get into the regime of the original training data size. So in like CFA, I think the number of examples maybe 50 or 60,000 in a training set. We're at least on like 10 to 22,000 examples we create to reach like the point where performance sets like converge, where you no longer see any gains, right? So this is kind of the ballpark that we've been playing around with. We haven't really tuned though. I mean, the thing is like these noise processes you put on top, right? Like they will kind of influence this a lot because the less amount of redundancy you create, like in this 2D example, maybe let me just go back. You'll see that like maybe you don't actually need all these examples. Maybe you probably don't actually need all of these examples here. I mean, clearly you need quite a bunch because this is where like there's a curve. But there's like, we don't have a check for like the synthetic example you create next, whether it's correlated with the previous one or whether there's redundancy. So I think there's a lot of room to like reduce. We really haven't looked into that at all.
So I guess very similar to what you were just saying actually. The difficulty seems to be finding the cutting points that are close to the area that matters in the decision boundary, right? So did you try, I know this breaks your assumptions, but did you try initializing points at the actual data and see what happens?
Well, of course, yeah, but like this is the thing, we wanted to go like really, really low on the assumptions, right? Like I do think there are a bunch of things you can do to make this better if you put assumptions. That's the interesting part. I'm always a fan of like you can put assumptions on top. I'm not so much of a fan of like you need to do all these things to make it work in the first place. If there's something where you don't need this to make it work, right? So no, you can do, like I said, so I mean one popular thing, like I said, if you know you have a neural network and maybe there's batch norm, you can minimize DKL divergence to like the batch norm, right? Like of the synthetic examples. That'll give you a lot of boost, for instance. Which is maybe what you're asking, like initialize at the training data, but in a less hard version. You're like even one step further
I'm
than
saying
that, right?
just to see if the like drop in performance is a property of your method or if it's a property of the initialization. I think
So we haven't tried your thing exactly. We did try the batch norm thing, and that does boost performance. So I would naturally assume that given that that kind of gets you closer to the data, your thing would as well. We haven't tried that exact thing. So like in this table, DI is like the batch norm thing. It's called deep inversion. It's a fancy name, but it's literally just going to say like query all the intermediate layers of your neural network. That batch norm puts out is like a Gaussian with like diagonal covariance, just minimize KL divergence of your synthetic example to that.
Yeah, just going back like maybe one or two questions. Something that actually surprised me was like the question about how much data do you need. I thought you would not generate the data beforehand. I thought you would generate as you go because you need to solve them, right? So isn't that like mini batching this distribution?
So yeah, this is a really good question. So you might have noticed a thing that we did, and I kind of subtly did it, and I never told you why we said that. We didn't call this like inductive knowledge distillation. We called it like extraction. And the reason we call it extraction is because of that thing. Like what we do is like we're not interlooping or anything. We're literally like saying there's a teacher somewhere, query the API, a bunch of times create a synthetic data set, use this as a new data set to train something. I do agree that if you have the ability to like now interact over multiple steps, there are lots of things you could do to make this like cooler or smarter if you have that access, right? Like that would be really nice. So no, this is like a very like, have the teacher do a bunch of queries, create a synthetic data set, go back to your standard mode of machine learning for the student.
Just a question. This must be a kind of ill-posed problem. In a way.
No, I was waiting for this.
No, okay, yeah. In the sense, in 2D is fine because the search space is so small. Go up in higher dimension, you have 50 features. Then they are real numbers, minus infinity to infinity. I can create something that make your student think it performs perfectly, but of course it's totally fair because the interesting part is just in a small part of the space. There must be you must kind of implicitly assume that you find this, or when you train it, then you should at least know what you're looking at. You know? One of the covariates is height in meters, and then you know it's in this kind of range. You have to do something, otherwise you can never make this fail safe. You know what you see?
Yeah, no, I know what you mean, and I think this is a
no, but then you say that it's all doesn't have any assumption, and because the assumptions are there; they are just implicit. You can take the same example. I can just move the features to to the moon, and you will not be able to find it. You know. So it's exactly the same thing, it's a shift, and your method will fail completely, I guess.
I know, I see your point.
That is not that assumption free that you kind of...
assumption free is a
It's
strong...
only assumption free if it works.
It's a lot less, it has a lot less assumptions than other methods anyway, but I agree with you. I think like this is maybe also the point where like this last part here kicks in.
Yeah, but you need to, so when you're doing the initial learning, you need to kind of code some kind of information that this kind of lives in around here, or this is about something, so you can do this. If this was just a black box, then this, you can never guarantee this works.
I agree, like we cannot guarantee it, of course. I do believe, like you said, exactly that like, if you don't need to know maybe like the training distribution, but like if you have some sort of...
No, you need to where to look.
Yeah, if you have some idea of like where the data lies, like that's why I said images, right? Like, if you understand that like...
That is not that assumption free.
It's not assumption free, but like I think like if someone gives you if someone uploads a pre-trained neural network on the internet, says this is trained on images, you probably have a good idea that this is like images they use normalized between 0 and 1, and like that adjacent pixels are similar. So those are assumptions, but maybe they're not assumptions on like, they're different kinds of assumptions, right? Like,
Yeah, but if there were just some kind of random features that you have no idea about, then
I think there are some kinds of data for which this is much harder than others. I agree.
I wouldn't phrase it like this. It's like you have to know something to kind of locate the area where this model is supposed to work. Otherwise, you're getting just out of just predicting where you have no data, and there you can fit things very good, you know, and then you think you're perfect.
That is a true point. I agree with it. Yeah.
Maybe is it okay so that you don't have any assumptions about the model, I mean, like the teacher's architecture model or something. Right?
Yeah, I mean, like I said, maybe here I'm using the terms a bit provocatively. Like they're probably not correct. There's like specific things where you don't need to make a lot of assumptions about, and others maybe where you do need to make assumptions. I think here where you can where you reduce the amount of assumptions people typically make is on the specific kind of teacher, and how you need to, not just teacher and how you access it. I mean, we also don't need to access, right? We need to access two things, inputs, outputs. So maybe just to look back, because I said I have a lot of time, but maybe now I have 10 minutes to get through that last part. I think we're not like truly black boxed anyway. Like we are assuming you are able to sort of forward through your model, and we're assuming you can differentiate with respect to the input. We're not accessing any like intermediate states, but that needs to be given. I do think it would be interesting, like don't scoop me, I'm just gonna say it anyway. I do think it would be interesting to, no, don't say it, okay.
Maybe I wanted to just, I think this is very closely connected to this convex duality stuff.
Okay.
What Thomas presented the other day. So, yeah, we know like how you can, when it's identifiable, when you can go between parameters and the data, but also there, you can only go up to certain statistics of the data, right? So you can only get the decision boundaries. And these questions are, as Cord said very rightly, that these are ill-posed. I think the community doesn't understand this. We should maybe have a discussion about this. We should write something nice.
I would love that. So actually, I was thinking of what to present here, and I wanted to present something else first, but then I thought like this would be nice to present because I want those discussions.
Good choice.
Thank you. But maybe just, maybe this is the worst choice now. Let's see. Let me get the last 10 minutes quickly on just, so coming back to the title, right, like challenging memory. So this was not really challenging memory. It was more like maybe sometimes you don't need to store the data. I do think there's a part where maybe if you were to store data, maybe sometimes it could hurt you. So there's this work that we've started doing, which I said Rajni is a poster, which is basically about the risk of confounding through continual learning, and specifically like through continual learning. So maybe continual learning creates some problems. It's just to recall, it's this paper, it's like called The Risk of Getting Confounded in a Continual World. So, right, just to get you back quickly, usually we do store some data. So a lot of people, what they do is they solve this problem by saying, let's get a core set of the green part, like I've explained in the tutorial, and then you're good to go. Now the question is this always a good idea? So we've created some data sets, and I want to try this out on you quickly before I tell you what models do. So it's a binary classification task. On the left you see like positive examples that adhere to a rule for generation. On the right you see basically negative examples that don't conform. Can anyone tell me what the classification rule is for this? Sorry, I think I heard it, someone. He's saying it's blue, right? So does everyone see that? Like left has blue, right one does not. So the rule is like blue. What about this one, this pair? Yeah, shiny, or like, in this case it's metallic, like that simulator allows you to simulate materials, so it's metallic, right? So, I mean, thankfully, you did exactly the thing I hoped you were going to do, so the test didn't fail. But
I thought about it, the brightness of the two sides, but I wasn't sure if I was.
you thought about it? Yeah, okay. So, I mean, this happens, like this kind of thing, like, so both things were wrong, I can tell you this much. That's the whole point of the exercise. But they're wrong in the way that like neural networks do wrong all the time, right? Like, so there's been lots of work on like spurious correlations, confounded features, simplicity pitfalls, whatever you may want to call it. Here's this like 2019 Nature example of the clever enhanced predictor thing, where I guess if you trained like a neural network on Pascal images, like a lot of the horse images had a photographer's tag on the bottom in the training data set, so later when you remove that in your test set, like it no longer predicts anything, because it kind of just capitalized on that like shortcut of the photographer's tag. Similarly, there are these works on like simplicity bias, like if you have these two clusters in blue and red, and you have two features, phi1, phi2, the decision boundaries that a lot of neural networks will learn is like this green one, this linear green decision boundary, even though it kind of ignores one of the features completely, even though both features are actually like equally expressive for this thing to learn, right? So probably the orange one is like a more meaningful thing to do. So like there is a lot of research on confounders, spurious correlations, shortcuts. They all frame it like slightly different, but it's like the same problem that we basically just had on this example where you said blue and metallic / shiny. So the data set we've created is like, well, it's continual confounding. It's basically the sequence of those things I've just shown you. So simulate data sets with like logical rules of how these are generated. They're like basic shapes and colors and textures, materials, and there's always like a true rule that you can use to classify everything. In this case, it's there's a sphere on this and a small cube in the positive set in every single image. So you can maybe see that right on the left column. It's always like a sphere and a small cube. But there's also always like a confounder present, like blue, metallic, large object. And so you could treat this as a continual learning data set and train on this over time and see what happens. Right? So basically it's a continual learning problem where maybe the task is actually the same, but over time the confounders change. So we were thinking of like news articles and so on, right? Like I was like getting inspired, like every time something happens in the world and like things change, like they dump on you something to distract you. So you're like not paying attention to it, but maybe I'm being malicious.
Sorry, you say confounder, but I can also say multiple solutions.
Yeah, so multiple solutions. So I mean, like, yeah, a confound. This is like.
But you're assuming that there's a truth, but you know, there's just multiple ways of looking at things.
Well, except I agree, but only for the partial set that you're seeing at that time, this is true. For the overall data set, it is not. Right? So this is the entire point.
Does it mean that you generated the data that way to know the truth?
Yeah, so we generate, this is a simulator, right? Like we set the logical rules we generate, and the first thing, of course, we're going to test in a second is joint training. Like what happens when you train on all of this together?
Like did you set it properly such that n goes really large so that you know that it's estimatable somehow? I don't know.
It is pretty large, yeah. I mean, we're not creating like 3 images, it's like thousands of images.
And the amount of noise that you put in the data in terms of confounders, they are small. Like in some way, you have a way to characterize that. And then if you play around with that, you get it right, but then you get it wrong. And there's a threshold. Do you do that?
You would have to ask Roshni that.
All
But
right.
yeah, there's like a 3-pager in the paper on like the exact logical rules of how to do it. Let me just give you the gist maybe, and then like I said, I'm just kind of sketching this to capture attention, which seems to work quite well, and then you can talk to Roshni at the poster.
Just to make it clear, this is like playing a game. I give you 3 numbers, 1, 5, and 11, and you're supposed to guess the 4th number in the sequence. And the problem is that you call it confounding, that there might be infinite number of solutions.
I'm not sure it's that, like...
No, you have all these games. I give you 3 numbers, 1, 5, and 11, and you're supposed to find logically the next one.
Yeah.
And then
yeah.
there is a problem that there are infinite number of solutions. So I guess one, and you say, I found another one.
Yeah, I mean like so, okay, I get what you're saying, like, these kinds of things that people do, I mean, they are very inspired by like Kandinsky patterns and like Bomba problems and like psychology kind of literature that basically all go back to these kind of things. This is kind of where this like draws inspiration from, right? I mean, so this is just a cartoon. So actually there are 2 versions of this data set, but for simplicity I'm only showing you one, because for the other ones I would have to explain like a lot of rules. This one's basically just saying like, right, positive set always has a confounder, and the negative set at that time doesn't have that confounder. It does not do any like restriction on whether that confounder can reappear in the future or whatever. So it's just like confounder thing 1 doesn't appear in the negative set at a time. And we can derive, paper and Roshni, that it's actually the way we've constructed it, the ground truth, meaning like the thing that's like sphere and small cube, if you train on the entire data set, is the like a priori most probable solution to learn. I can show you this empirically, like if you...
How more probable is it?
Okay, this how more probable I can't tell you. So you can see, so I'm going to show you as a final thing like this table. It's going to show you three basically sets of columns. There's like this current task accuracy thing, right? Like so you chunk it. T1, T2, T3. This literally just means like how does the learner perform on that subset at that time. There's an old task accuracy, and it's It's basically telling you what is the performance on the first task at the end, what's the performance of the second task at the end. And then there's an unconfounded accuracy, which means how does this perform on like the actual data set that just does it, the test set that doesn't have confounders. So to test like did this get confounded or not. You can see if you train jointly, so jointly meaning you just train on the entire data set, it has these metal confounders, blue confounders, and so on, you'll do decently well at each individual sort of subset, and you'll do pretty well with the neural network on this entire data set, even on the unconfounded one, right? The one that doesn't have these spurious correlations. And now Empty's left when I critique his method. No, not yet. The two things that people usually look at, so you can look at the naive sequential thing. Naive sequential meaning you do this like stupid continual learning thing where you train on T1, then T2, then T3 in sequence. You can measure the performance on each of them individually. Not surprisingly, if your model is large, then your network is going to be 100%. And you can check sort of basically, has it forgotten the intermediate solutions? Yes, it has. It's quite 50%, right? Like it's, I mean, there's a plus minus I didn't leave out here. I left out here for simplicity, but it's like, it's just random chance guessing. And it's also performing super poorly on the unconfounded set. So it's basically all it's doing is it's memorizing the confounded solution in each individual subset, and it's just failing. It's forgetting even about the old confounder, and it's not solving anything. And now you can look at all the continual learning methods where there's this, oh, Siddharth, I'm just kidding. No, I mean, they all look bad, to be honest. And the reason they probably all look bad is that this is a scenario they probably were never designed for. But interestingly, and this is the point that's like interesting to us in the next one, so some of them are regularization based, most of them are memory based, like memory in the sense of like store a subset of the data and keep on training on it. Some do both, like from, they will actually maybe forget a bit less, but they'll still forget and they'll be very poor on the unconfounded data set. So the logical thing to try is, well, have we maybe just set the memory size to be too small? Like, are they just bad because there's not enough memory? So what if you gave them like full memory access? Basically train on T1, continue training on T1 plus 2, continue training on T1 plus 2 plus 3. And you get maybe sometimes what people call like cumulative or like a cumulative learning. And now the thing you'll see is, this one is usually assumed in all of the continual learning works to get you the same thing as the joint training. It does not, right? So training on the joint data set or training on the data set on all the data items in sequence doesn't give you the same thing, and especially on the unconfounded data set. It now starts to perform very poorly. So joint training kind of gives you the full solution because it's able to sort of ignore the confounders. But when you introduce the confounders over time, your system suddenly gets confounded because of this, because like this temporal sort of idea, right? So we can talk about this in a second, but basically we call this like insidious confounding because it's insidious in the way that it's introduced through the time aspect in a second. And like I said, there is a second version, it's on the poster, you should talk to Roshni in the afternoon. There is a second one which is like a disjoint version, which has different logical rules of generation, which is also very interesting because you're gonna get a table that looks pretty much like this, where these forgetting values are 100%, like they don't forget, but they still suck in the unconfounded data set, they'll get random chance, because what happens is they'll basically create solutions that are like concatenating the solutions to the confounders. It'll be like the solution's gonna become like, oh, it's true if it's blue and metal, and like, it's just gonna do that kind of thing. So you should talk to Roshni about that, but also maybe we thought this might be an interesting testbed to challenge a bit this idea that is like it's just in the air and continual learning that everyone assumes you always just need to accumulate everything, and if you store all the data, there's no problem. And well, even if you store all the data over time, it is a problem. Like joint training maybe is not, but storing data over time can be problematic if there's like conflicting, contradicting information in there. So maybe continual learning is also much more complicated than what people sometimes assume. So, right, conclusion, right, we're basically done. But the TLDR is with respect to memory, the whole abductive knowledge distillation thing was basically supposed to say that maybe sometimes we can get away without even like storing data or doing away with the data. And then the insidious continual confounding thing is the opposite. It's like maybe even sometimes storing the data over time can be hurtful. So thanks for your attention.
Given that we started 2 minutes late, we have 5 minutes.
Awesome.
And coffee, so.
So I wanted to comment about the data that we produced that you looked at and that we sort of been almost like white noise.
Ah, sorry, you're like way back. This one,
So,
yeah.
Yes. So why does it, I mean, do you not apply the total variation regularization here? Or do you? Because in deep green, they did produce somewhat distinguishable data points where like the data is somewhat interpretable.
The difference though is that in deep dream, they're like really maximizing the confidence hardcore, right? And in our sense, the contrastive thing is basically gonna, like in the binary case, gonna pull your vector to something like 0.49, 0.51. It's supposed to be like really close and just a tiny bit more in one class. So it's not gonna produce these like very dreamy dogs and so on. Because it's not like 100% dog, it's like
How do they know how much to push?
hyperparameter.
So this does include the total variation.
I think so,
Okay.
but I wouldn't bet money on it. I think so though, yeah.
Yeah, can you show that the comparison between cumulative and dot? Like, from an optimization point of view, what's the difference between cumulative and dot? Like, it's like initial value, like T, when you start from T2, T2 from T1, you initialize that at T1, right?
So yeah, so joint is like you just take 1, 2, 3 all together, shuffle it, IID, train on it. Cumulative is basically like you train T1 only, you keep the weights, you continue training on T1 plus T2.
When you compare T1 plus T2, you shuffle from T1 plus T2.
Yes. So like the training is always like shuffle, you assume IID and so on. It's just like you train on one thing first, and then train on the next thing together, and the next thing together.
It has
It's
a
like,
bit more history.
it has more history. It's like from a data set point of view, it's literally just concatenating the data sets and keeping the shuffling and everything.
Then when you arrive T3, you are exactly doing joint training.
Well, that's the point, but now you have history. So this is the problem that continual learning people always assume. They say like cumulative is upper bound, it's the same as joint training, it always that's the same thing. No, it has history, like the order and stuff, like it all matters.
But the upper bound is correct.
Eventually, maybe.
Yes,
You
the
said-
upper bound, sorry.
You said upper
Yeah,
bound.
I critiqued the wrong thing. The upper bound part is correct. The part that they assume it's the same as joining,
That you
like,
actually
that-
the
yeah,
upper bound,
yeah. That is the part that's problematic, yeah. Right? Get it?
You may not, it's this warm starting in neural network is all messed up. Maybe have to think about that way. Right. If you start in the wrong place, you may never reach the solution, you know?
So the initial value.
Yes, like that, yeah. That's
Yeah,
one way to
yeah.
think about it.
Yeah.
Any other questions?
Thank you for the talk and also congrats on the ASTAT prize.
Thank you.
Okay, so I understand your deep mimicry is data free. Okay, if you're going to apply this to continual learning setup, how do you make it memory free?
Well, I mean, in the naive way, we're just creating a synthetic data set, right? So you train at T1, you create a synthetic data set, and you do like the thing that people do in replay all the time, like you shuffle it together with your new data set and keep on like training on it, right?
So are you going to basically accumulate your synthetic data set during time?
Well, I haven't done it yet, or we haven't done it yet, but like I guess the most naive thing that you would try first would probably be that.
So I guess if you have one more task and then you do this every single time, right, then more or less you're accumulating a memory, am I right?
Well, that's the question though, like, I mean, you could think of accumulating this, but technically speaking, you could also just create a new set of synthetic examples then again later, right? So this is a tough, like, problem, like, I think the continual learning community is a bit divided, even if you have like a generative model, it's the same question. Like, do you generate the data, you store all of it, or do you generate the data, train on it, then generate the new data. People often don't do that because you get like snowball kind of errors in there, and they like rapidly accumulate. But yeah, there's all these like nuanced variants that you could try out now, right? And maybe there's something even smarter to do if you have better suggestions.
Okay, thank you.
Any more questions?
So basically, I think this is really a cool idea, but I think at least from what your explanation is basically you actually assume that what you want is just a decision boundary, right?
Exactly.
Well, that's why I said it's abducted, yeah. I mean, yeah.
So basically it means like, it's kind of like, this is in some sense an assumption, right? It's basically saying, what you only care about is decision boundary. And for example, if you're doing like regression case, probably that's correct, right? And or if you somehow train the thing with like, I don't know, some kind of variety, and then you want to keep like the posterior.
Well, yes, of course. I hope I said the word classifier like sufficiently many times to kind of say that. But okay, I mean, I was not, yeah. I'll just say it, it's okay, like, you can cite it so. There are a lot of unsupervised learning and like even transformer models that no matter what they do, even if they want to generate, they'll classify, like, next token prediction. It's a classification problem. Like unsupervised learning, like autoregressive sampling an autoencoder. So like it reframes the reconstruction of images to like a uint8 255 way classification problem. So you'll find like a lot of ways to reframe into classification problems, and maybe this would be helpful.
All right. Well, that was very nice of you to have so much discussion. So really appreciate that.
I learned.
Yes. Thanks for your presentation. So let's again give it a big hand. Okay. So our next speaker is Siddharth, and Siddharth has been working with us for many years actually. When he was doing his PhD. So I'm very happy that he's here. He's currently a postdoctoral fellow at the Data to Actionable Knowledge Lab at Harvard University. And he works on probabilistic deep learning. Actually, he works on Bayesian deep learning, let's say, on a broad range of problems like knowledge adaptation problem, like continual learning, federated learning, knowledge distillation. But he's also been working on interpretability, privacy, biases in LLMs. He did his PhD in Cambridge with Rich Turner, who many of you may know. And he was awarded a Microsoft Research Award and an honorary Vice Chancellor Award from the Cambridge Trust. So thank you for being here. And he's going to talk about federated learning.
Okay. Yeah, it's great to be here, see you all. I'll be talking about federated learning with the Laplace approximation. This is a very recent work with MT and Finale Doshibales at Harvard. And please do ask questions whenever you have them. Quick talk outline before getting into the main meat. Start with some background. What is federated learning? What are some previous methods to federated learning? I'll explain what targeting global loss at local clients means. And then go into some Bayesian methods that exist for federated learning. And that we're going to start with those Bayesian methods and derive FedLap, which uses a Laplace kind of approximation to existing methods, and show how it's actually related to many previous methods in federated learning, not just Bayesian ones. And that'll allow us to get some insights into why some of these previous methods work, as well as some improvements that we can then make. We'll also derive a function space version, which is going to link quite nicely to memory-based continual learning ideas. I've done a lot of work in continual learning, not so much in federated learning in the past. We'll end with some experimental results. Okay, so what is federated learning? Federated learning is interested in this setting where data is distributed among many different clients and it's distributed heterogeneously. So you can imagine many different clients. Each client might be like someone's mobile phone, and they have their own data on their mobile phone. So that's one option. Another option might be like large institutional databases, like hospitals. So you might have each client is a different hospital. Each hospital has its own patient data. you don't want that data necessarily leaving that hospital. In hospitals, it's often not allowed. So in federated learning, the security of data is very important. This data must remain within the client. It's not allowed to leave. And the aim is to have this global server that exists, that communicates back and forth with each of the clients, and you want to learn a model at this global server without ever sending, as I said, local data to and from the server, because the data is not allowed to leave each client. You want to do this while minimizing communication cost. So we assume in federated learning that it is expensive to communicate usually model parameters to and from the global server and the local clients. So let's try and learn a global model as quickly as possible, minimizing this communication cost. Examples of this, I've already given the hospital example. Other examples that people, I think, do use is like voice recognition in Siri, I believe. You never, like your own, Apple says that your own voice data never leaves your own device, so they do a federated learning kind of setup. Also, next word prediction with keyboards on your mobile phone, like with Google, I believe is learned in a federated way. And I'm sure there are many more examples, maybe some of you know. But I don't.
Scaring me now.
We hope there are many more examples, yes. Let's formalize this a little more so we can look at some methods. So aim is to learn, as I said, a model at the global server. We're going to call this WG, so this can be like a neural network. And you want to learn this efficiently and securely from private data sets, DK. So I'm going to say each client, little k, has a data set D little k, up to big K clients. And the ideal global model that we can learn, sort of assume, we're going to call this WG star. It's as if we had all of the data in one place. Obviously we don't, but if we did, that's the ideal model. So that's this minimization of this loss function where you sum over each of the clients' losses, and L sub k of W is the loss over data in that client k. And I've added an L2 regularizer with hyperparameter eta here as well. But actually, in the current literature, basically all federated learning methods take eta equal to 0, no L2 regularization. I'm going to call this ideal WG star eta equals to 0. Recently, in the last year or two, there have been a few papers that have started realizing that eta not equal to 0 is actually really important and helps learning quickly in federated learning. So this that is a benefit of our method, as you will see later. We will have an eta not equal to 0, which is helpful. There are 4 steps in the most simple way of federated learning, and for the rest of this talk, there's 4 steps, and you keep iterating this until you converge. So in step 1, you take whatever WG you have at the global server that you're learning on, you send it to the clients. Step 2, you use that WG and whatever data you have at the client to learn some new parameter at that client, WK. Step 3, you send those parameters back to the global server. And step 4, you combine them in some way to learn a new WG, and then you repeat. You send that new WG to the clients, and so on and so on. And I mean, you can phrase this in different ways, like instead of sending WK back, you can send a delta, a change in parameters back, whatever, it doesn't matter. Mathematically, this is what's going on.
So how about this sequential? Can you send to several same time and you get it back at different time points, and while you're processing this, you also get one.
Yes.
So then you're just all right. It's a kind of, if you're implementing this in parallel, is it like a critical?
So there are a
where
few.
you process the answers.
Yeah. So there are a few different setups in federated learning. So you just described an asynchronous setup where you send to everyone different clients. Well, these are all different clients, so they might have different size data sets. They might take longer to train, shorter to train. And then you asynchronously receive updates from the clients, and then you update this WG. And there are various methods to deal with that, but I'm not going to get into that at all in this talk. In this talk, we're going to assume it's all parallel. So you send to all clients at once, not just a subset, and then you wait until you receive an update from each of the clients back.
Then you process each one of them kind of sequentially, and when you've done all that, you send it out to you.
It doesn't have to be, so we're not going to do it sequentially, we're going to do it in parallel, as if we get, wait till, but yes, essentially, wait until you get all of them, do an update, and send it all out again. Yeah. Yes.
Just to clarify, if WK is the gradient of dataset D2 or DI,
Yeah.
DK, and then the combination is just addition of these gradients, then you would get just gradient percent?
Almost, and later we will see it, but so if WK was just the gradient, then if WG was WG old plus the sum, then yes, that's just gradient descent. Of all of the
Then you
data.
get the ideal.
Yes,
So-
then you will get ideal, but it'll be really slow. Minimization costs will be, communication costs will be really high. And that's the problem. So we want to improve upon this like very simple baseline, which is just gradient descent, but communication inefficient.
So here you're explaining how the learning works. Apart from that, there is also like how the model is used, like the inference. So I believe as you're saying that the data cannot leave the client host device, it means that the inference must happen on device. So the model is small enough to actually do it on device. Nowadays we are getting it well, so for inference you have to kind of use the server. That's not what happens in the learning.
Yeah, here, so as I set it up, we're only interested in learning this model, WG. Yes, if there are mobile phones and you want to use the model on the mobile phone, that model needs to then eventually be on the mobile phone. Same with hospitals, same with anything. Yeah.
You said one of the privacy requirements that DK is not available to the student. It seems like some DK is going to be
Yes, so I like to pull apart security and privacy. So security, I'm sort of thinking of the data itself never leaves the device. Privacy then gets into these arguments of can you recover the data given some model parameters, for example, and of course you can, especially with neural networks. So then, yes, there are a lot of works that look at differential privacy plus federated learning to ensure that also cannot be done. This paper, we have not applied differential privacy to anything, can be, but we haven't, just like an add-on. Right. I want to have a quick slide on connections to continual learning, given the workshop and my previous work. So how is federated learning similar? So in continual learning, data is split temporally, and Martin's just talked about it, and so on. So data is split temporally, not spatially. What that means is, you see data D1 first, then D2, and so on up to DK. But you only see them one at a time. Federated learning, the data is still split, but over clients. And in fact, you can see that federated learning recovers continual learning if you constrain it to only go through each client's data once in sequence. So you sort of learn on D1 first, then the global server learns something, then it learns on D2, client 2, never allowed to look at D1 again, then it learns something, and so on. So that is continual learning, but federated learning can therefore be seen as, I don't know if it's a generalization, but I view it as potentially easier than continual learning, because you can revisit clients. And because you can revisit clients, you can sort of use information from the other clients to sort of slowly improve upon places you might have made a mistake before. This is not really possible, well, it's not possible in continual learning. Once you make a mistake and you sort of commit, if you commit to it, you've committed to it.
I think generalization is bad.
Yes, I shouldn't have said the word generalization.
It's beautiful. It's not the right thing.
Yeah. I'm going to go through some methods so you can get some intuition as to like simple ways to do this and then more complicated ways, and how that's going to relate to our own method later. So federated averaging, it's a 2017 paper. It's sort of the first one that kicked off federated learning as a field. So we're going to look at the update locally. This WK is very simple. You just minimize the data, like the loss over the data on that client. And at the global server, you just weighted average all of the WKs. So here n sub k is the size of the dataset dk, and n is the full dataset size of all of the data. So it's just a weighted average of all of your WKs. It's very simple. Here, you don't actually perform this argument locally till you reach a solution with to the full minimization. You do some sort of approximation. You only do a few update steps locally, actually. And if you only did one gradient step here, then you would recover full batch gradient descent. But if you do a few gradient steps locally, then it's not quite the same as gradient descent, but overall at the global server, but hopefully it'll require fewer minimization steps, maybe not, fewer communication steps, maybe not. And that's kind of the problem with federated averaging, because if you take too many steps locally, then all these models start pulling further and further apart locally, and then you try and average them, and it doesn't really make sense to average things in parameter space when there's so many local minima, and it kind of doesn't work. So it's sensitive to the number of local iterations taken. So people have tried to improve upon this, of course. A very simple improvement is this fedprox. Fedprox just adds another term to the local client minimization, just to push the minimization towards being closer to WG, whatever WG it received last time. This allows you to take a few more update steps locally, so a little less, it's a little more robust to the number of local iterations you take. But still not perfect. I think the ideal thing you want to do is to target something such that the WK that you learn when you minimize whatever local client is equal to WG at whatever stationary point solution of the entire algorithm. If you have that kind of property, then you can just minimize at the local client for however long you want, or however, the longer the better, and then you will still get something good. Yeah.
From a naive thought, each time the global server I'm averaging on the local ones. But if I move slowly from the previous WG toward the average,
yes,
that makes sense.
That does make sense. People do this. They call it fed opt. All methods in federated learning are fed something, which is great.
I'm fed up. Is there fed up?
There is. That is totally possible, and then that does help as well, but only slightly. It's still very sensitive. The overall performance is still sensitive. Again, less sensitive than it used to be to the number of local iterations. These are all ideas that help. I didn't discuss that one specifically, but yeah. So the class of methods I did want to go into detail about are these ones called fed-ADMM. It's sort of a federated version of ADMM, sort of an older method, alternating direction method of multipliers, something like this. And these do target something locally with the properties that we want. So they're motivated through, there are actually a bunch of methods here, but they all look actually the same fundamentally. They can be motivated through proximal dual relationships, ADMM, or the dynamically matching parameters, but the overall update equations are the same. And the key part is basically we've added this second thing to do at the local client. So I've called it a VK. You can view this like a constraint or a Lagrangian constraint of some sort. Or however, that is one way to view what's going on. And it basically ensures that WK is equal to WG. And then sort of it changes the global server update in some weird way as well, which I sort of mathematically pops out from ADMM. Yeah.
So do they have any interpretation on this delta? Or V, I guess, is the Lagrange multiplier. Do they call it that?
Yes. So I've listed 5 papers here. I think maybe the first one and these 2, 3, and 4. I don't remember which ones, but yes, some of them do.
And then delta is just something.
Delta is just something. It is in,
Sorry, no, I don't know about this, but I have another question.
okay, so yeah, so delta is just a hyperparameter that needs to be tuned, and people don't really know what it means, whereas we are going to give it some meaning.
It's a bit of a naive question, but this ADMM methods, they're from the 60s, so they are in Bertsekas, PhD thesis.
Yeah.
So I don't know what's new here. I mean, that's
that guy.
No, but it just looks like I mean, yeah, of course.
No, you're right.
That question, but I mean, just.
So
It's a new name.
I need to look at these papers again, these ADM 2, 3, and 4, but I think it's not straightforward to immediately apply ADMM to federated learning specifically. So they had to make a couple of small changes to do that. I think like the global server or something, this is required some, I agree with you, it's relatively small, but that is what it is. But you're right, these are, ADMM is old.
But I guess it's obvious, no? You take the stationary point of the objective, then the gradient should be 0. So you get that relation.
There are loads of ways you can combine things here. I mean, it's obvious to say that at the stationary point this is correct, but you could have, this doesn't need to be 1 delta, for example. Or you can do lots of different things to have that property still holding.
Do you have time for questions, or are you running out of time?
At this rate, I might run out of time. Thanks. FedDin, which is actually the 5th paper in that previous list, changes FedADMM from the other papers to perform slightly better, and I want to mention that because our method is going to look a bit more like FedDin. So FedDin empirically performs better than all the FedADMM methods. It makes, I think, 2 big changes. So firstly, instead of having a delta here that is global, it has client-specific delta k, which is proportional to 1 over the client dataset size. And secondly, it adds a local weight decay loss to the loss here. So with one more additional hyperparameter than it's tuning. And what we're going to see with our method, we're going to naturally recover change 1. They never theoretically or anything say why that's a good idea. It actually only just appears in the code base, not in the paper either. So we're going to naturally recover that, and then point 2 we're not going to need at all. We're not going to have this additional hyperparameter. And that's going to be because FedDin and all these other federated learning methods target this WG star eta equal to 0 that I was talking about. There's no L2 loss at the global optimal solution, whereas we are going to have something. And so I think that's my intuition as to why we are not going to end up needing additional local rate decay. Cool. Okay, I'm going to move on. I'm going to pause that strand of previous works and now introduce Bayesian federated learning, and then we're going to see how they're related. So Bayesian federated learning, so I've just written out Bayes' rule here, but in the federated learning setting, so the true posterior is proportional to the prior times a bunch of likelihoods. Just factorize the likelihood to be over the data from each client k. And the aim is to learn, our approximate posterior. And again, so in federated learning, these couple of papers, for example, assume that the approximate posterior factorizes in a specific way, specifically that, well, we're going to keep the prior the same as the true prior, and we're going to have what they call site parameters, T sub k and W. Each one is going to try and approximate each likelihood. It's very similar to expectation propagation as well. Standard variational methods, we're just going to assume things are, we can just assume things are Gaussian, and in this paper, like in this work, we are going to say that. So if things are Gaussian, sort of, we assume the prior is Gaussian, we're going to posit Gaussian distributions, T sub k, side parameters as well. I'm not going to go into too much detail about these equations. I just want to point out the overall high-level takeaways about how Bayesian, so particularly partition variation inference, which is a Bayesian federated learning algorithm, looks very similar to the previous FedADMM, FedDin methods we had. So you can see there are still 2 equations. One of them is some kind of local minimization, another one some kind of something equal to something else. We still need to store something locally, like in FedADMM, unlike the Fed averaging, but like FedADMM, there's a second equation you need to store these T sub k's. And also PVI has this property that a stationary point of this algorithm is a stationary point of the global, like the full global VI solution, global VI loss. Just a couple of things to point out here. We've got these T sub k's. Remember, T sub k is each client's contribution to QG, to the global approximate posterior. So it's kind of nice in PVI, in these Bayesian methods, you sort of just simply multiply together the T sub k's to get your Q sub G. FedADMM had something weird going on there instead. And for those of you who are more familiar with EP, you can see that this top line, this right-hand side of KL is the tilted distribution. You start at your current global approximation, QG, you remove the old contribution from that time, T sub K old, and you replace it with the true data likelihood, P of PK given W. Now EP has the reverse KL, but PVI has the KL in this direction.
But they're also natural gradient.
It can be, yeah. Yeah, yeah.
I mean, here people are not familiar with natural gradient.
Okay. Yeah, well, the concept of tilted, I guess, people use most in EP, but yeah, so this can also be done like natural gradient where this row is like a damping level. That's the next thing.
There's no problem with the prior here, that is kind of amplified and because if you added the stereo.
No, prior is all good. Prior gets taken care of correctly because prior is here and T sub K, each T sub K is
because someone is better at learning, they use the same prior for every phone and that together, but they should use
they should use one every K.
But because there is a stereo, yeah, so this is okay.
This is okay, absolutely.
So I don't know, maybe I'm missing this, or maybe I don't understand the PK yet. So, like, if I think back to the mobile chat example of the competition, is this gonna basically like flush out my individual preferences according to like the mean of the average? Like maybe I have a very different way of speaking than you do, and it seems like the autocomplete is just gonna do what the majority of people does, or maybe I'm missing that part of it.
Not quite. So here the TK is it's an approximation to the likelihood of your data, but only in the context of all the other clients. So think about it. This is getting a little nuanced, but I won't get into all those details. That gets very complicated. So yeah, it's an approximation to the likelihood, but because this approximation is Gaussian, it might not look very good by itself, but in combination with everything else, it works or should work.
Okay, so don't want to take too much time from you, but I want to make a point that people love EP in the UK, right? Come on, you're writing KLQ something, right? It's not EP.
No, this isn't EP.
Yes, but you shouldn't say that this is it's variational inference actually, right here, right? So when you say what is T, then it's of course it's natural gradient. It's exponential of lambda tilde is what I call, right? So I think why we bring in EP when we are actually doing variational inference? Let's not do that.
Okay.
One very quick question. What is rho?
Yes, getting to that now. Excellent question. Rho is a damping factor, so you can just set rho equal to 1, and it thinks of this is just like a hyperparameter. Like past work has found setting rho to be 1 over the number of clients works well, and that's what I will do as well. Like, I'm not going to try and tune this, but it's just a damping factor to make sure things don't change too quickly.
And if you set it differently, you will not converge to the correct solution.
No, you will. You can set rho however you want. You will still converge to whatever solution. But if you converge, you will converge to a correct solution. If you set rho too high, then you may not converge. So we're now going to simplify this algorithm. We're going to do the Laplace approximation, and we're going to find something that looks very similar to FedADMM methods. So I'm going to start with a local update. This is that KL that we had, KLQ to the tilted. We're going to do two things to start off with. First, we're going to add a local prior, PK, and this is going to come in to be over here to be multiplied by the data likelihood. Why do we do this? It's sort of, it allows, well, firstly, it makes the equations look much more similar to Federated, so it's sort of drawing parallels to existing work. And secondly, it sort of stabilizes training, or it doesn't stabilize, it wasn't unstable, but it makes training a bit quicker. And it's completely allowed because we can just subtract away the additional priors that we added in when doing that global, the global update later. The second thing we're going to do is approximate the KL expectation with respect to Q of W to be at the mean W, like the delta, first order delta approximation, this kind of stuff. That's going to get rid of this expectation with respect to Q to be an argmin with respect to W. It's going to give us this. Again, it's actually not anywhere near as complicated as it looks. I'm going to start on I realize it's a bit low for people on this side. I'm going to start on the third term. So the third term is so we've assumed Gaussian, so the third term is that QG Gaussian, which is that first term here. The second term here, we're removing the contribution of TK, so it's the subtraction of the old site distribution TK, and this term likelihood prior is the likelihood new prior that we added. That's all that's going on here. It sort of looks a bit complicated with sigmas and so on. Oh, I didn't add it in. The number one that we did here was add in the prior. I didn't write it. We're not going to get into these equations. This first equation is the same as before. My point of writing out the second and third equation is just to say that we are just multiplying and dividing Gaussians, so we can do this in natural parameter space as simple additions and subtractions. Not really important what it looks like, but it's very simple to write up and do. So this is then a method which we call FedLab-Cov, because there are covariance matrices floating around everywhere. All these sigmas make things look a bit complicated. We're going to get rid of those in a bit to make things look a lot simpler. But there's one more slight detail that needs to be pointed out with FedLab-Cov, and that is, well, we've learned these WKs, then we need to calculate the covariance at WK, and we can do that in a Laplace kind of way. We're going to calculate the Hessian at WK of this objective. And for that, you need to do some kind of approximate Hessian probably. So, I mean, in experiments, we're just going to do diagonal Gauss-Newton matrix, but you can do whatever. So let's simplify these equations. Let's make an approximation. Maybe it's a bad approximation, but it's an approximation. We're going to approximate all of these sigma inverses, the precisions, to be equal to delta. And then that means that we can get rid of all of these complicated things, a bunch of things cancel out, and we end up with FedLab, which looks like this. So I say this might be a bad approximation. It probably is, and then we can obviously improve the method by not making this approximation, doing FedLab-Cov. But also, this is sort of similar to ideas from Bayesian learning rule from MT, where to recover SGD or something from the Bayesian learning rule, you do exactly this. So here's the final FedLab algorithm. Same things as before. You've got your global distribution. So remember, this now looks quite like what we had before, with like this W minus WG squared. Subtract away the old site distribution and add in the true data likelihood with our new prior that we've introduced. You've got this VK update here, which something looks similar. I'll make it exactly what's similar more clear in the next slide. And then at the global server, we've got this simple addition of the VKs. Now the VKs are the site parameters, so we're just adding them together. And the nice thing about FedLab, similar to FedADMM and FedDin and PBI, and all of them, is that at a stationary point, once this algorithm converges, wk is equal to wg is equal to wg star. The difference now is that we don't need et equal to 0. The previous methods, the non-Bayesian methods, always had et equal to 0. This L2 regularizer at the global solution being 0. Not the case with us. So I've now rewritten FedLab to look as similar as I could possibly make it look to FedADMM, so we can look at the differences. I'll go through them one by one. So one difference to FedADMM at least is the fact that we have delta over nk, not just delta. And then remember I said this is something that FedDin did before. So we sort of recover that, the thing that they did to improve their empirical performance. We have a damping factor. Previous methods did not have a damping factor. Or they set the damping factor equal to 1. We just set the damping factor equal to 1 over k, like in Bayesian works, but that is something new. The global summation at the global server is different. Earlier we had some additional plus WK, some weird things happening at the global server, which to be honest, I don't have much intuition for. Here we're just adding together the site parameters. Not just that, but something that pops out is that
natural gradient.
Okay, natural gradients. And something else that pops out is that the delta, this delta hyperparameter that exists in our method, is actually equal to eta, the L2 regularizer of our global loss that we're targeting. So that gives us some nice insight into what delta is doing, even in FedADMM methods, which is slightly different, but at least in our method, it can help us set that value of delta instead of just tuning over the entire whatever range of deltas. And remember that in practice, FedDin required an additional local weight decay term to do well, and I'll show you how it does badly without that, whereas we don't need that additional local weight decay or its additional hyperparameter. So here's just a quick graph to show how important that local weight decay is for existing methods, specifically FedDin in this case. So before looking at the graph, actually just tell you the setup of this experiment. This is homogeneous MNIST, which means that there are 10 clients. Well, there are 10 clients and each one of them has a tenth of the data chosen homogeneously. So it's like a very, very simple setup. Just like a 2 hidden layer, multi-layer perceptron. It's actually a very simple setup. Everything should perform really well. So you'd hope. If you see the blue and red lines here, so the red is FedLab and the blue is FedDin with a sort of a tuned optimal local weight decay, you see that they perform very similarly. But without local weight decay, which is this light blue cyan color, you see it sort of just falls very badly. So it somehow does okay at first, but then it just gets worse over time, over communication rounds. And with suboptimal weight decay, so here it just changed from the optimal weight decay by an order of magnitude in both directions, sort of see that FedDin also doesn't perform very well. Yeah?
What's a communication round in this case?
One communication round is so the global server sends WG to the client does whatever client sends.
How often do you communicate? I mean, like, is it like every mini batch? Is it like once on the entire data? Or?
So one communication round is one pass through all of this. You do it all local clients in parallel, and then you do this to all local clients in parallel. You do this, you send all the V tilde Ks to the global server, do this update.
So you communicate everyone?
Yeah. So yeah, so one benefit here is having removed this additional weight decay term entirely. We'll look at experiments in a bit to see the other benefits, but now I want to just have a slide on how to include function space information in this entire setup. Call this FedLab func for function space. And it's actually the reason we do this is that it's sort of inspired from memory-based continual learning work that others have done, we have done in the past as well. So we're going to be sending predictions over inputs, that's what I mean by function space, between the local client and the global server. This makes a strong assumption. This assumes that there are some inputs that are shared between that global server and the local client, right? This is an assumption that there's a newish field called federated distillation that makes this assumption. They sort of assume that you have a public data set available to everyone. So we're making that same assumption. Just a very quick sort of high level as to how we do this. First, we have to rewrite the global server update as an optimization. So sort of sum together each of the, so earlier in memory, it's just a sum over VKs, basically. Now it's something a bit more complicated. It's a sum over all the contributions from each of the clients, and then the prior term also comes out here. If you optimize this, you actually recover the same thing as before, but now they've written it explicitly as an optimization problem. And then we're going to add in a loss over inputs in what I'm calling MK, because that's what we called it in continual learning, some subset that of some inputs that we're sending predictions over. This additional term here, we're going to send over prediction over input I, or just for the y hat I, and there's a loss term over that, so we multiply it by some factor tau. And the way that we derive this exact update is sort of very similar to k-prior work, as well as improved k-prior work, which we'll be talking about tomorrow, but had to make some changes to make sure it fit with federated learning, basically. And I haven't written it out to avoid yet more equations for you to look at, but a similar term to this is also included in the local client updates. You have to remove the contribution, alpha contribution, make sure everything's done correctly. Cool. Any questions before I go to results? Right. I'm going to start with some results on very simple logistic regression. Going to look at federated averaging, fedprox, fedin, fedlap, fedlap, cog. Going to look at two data sets, Flamby-Hart and UCI credit. So Flamby-Hart is like this federated learning benchmark, which is sort of from this paper that proposed a bunch of benchmarks. For federated learning, it's taking data from 4 hospitals to try and predict heart disease. And sort of naturally heterogeneous in that it is actually data from 4 different hospitals, and they have slightly different client populations, like patient populations. And UCI credit, well, there's this UCI data set where you want, again, binary classification to predict defaulting on payments. We're going to take a very specific heterogeneous split from previous work from PBI, so there's 10 different clients. And sort of it's split in such a way that the 5 clients have a lot of data, 5 clients have very little data, but the label distribution is done in a difficult way, basically. It makes life difficult. Then we're going to look at accuracies after 10 communication rounds, 20 communication rounds, and so on, just to compare how these different methods do. Also numbers. I just want to focus on fedin and fedlap to make the point that fedin and fedlap are very similar to each other always, even though fedlap has one fewer hyperparameter, basically, and has these slight differences. So the point here is to say we might as well use fedlap. It's easier to tune and so on. Yes. It's the local weight decay. So there's one few hyperparameter that is the local weight decay that you need in fedin to do well.
So it's actually much fewer parameters. It's always fine.
Good point. So in fedin they just use the same local weight decay for all clients. They don't tune different ones for each client. Yeah, so it's one fewer because that I haven't actually even tried having different local weight decays. I don't know. The second point I want to make is, if we look at FedLab-Cov, that does better than FedLab and FedDin. So after 10 communication rounds, it's doing better, after 20, it's doing better, and so on. One thing to note here is that FedLab-Cov requires, each communication round requires sending twice the number of parameters than in all the other methods, because you don't just send your mean, your WKs, but you also send like this diagonal Gauss-Newton matrix, so another vector of the same size, which is like this Hessian approximation. So it may not always be a good idea to do this if that's too expensive, you know, or it might be fairer to say, instead of, papers do it in different ways. Some papers, instead of doing communication rounds here, so after 10 communication rounds comparing performance, you might want to say after communication cost, and if you want to compare performance after communication cost, then communication cost of this is equal to 20 rounds of any other algorithm. Yeah.
How do these compare to the ideal that you mentioned?
Oh, good point. I didn't write it. So the ideal here is, I think, 80%, maybe it's 80.5, I don't remember. It's in the paper, I don't remember. And here the ideal was, I think, around 88.5 or something percent, 88.3 maybe. So it's not quite reached it in this setting. Only FedLab-Cov has at the time.
And in the case of FedLab-Cov, do you measure the ideal to be against the patient?
Good point. I did not. I should. Yeah. Should be against the Laplace version, should be the correct one here. Yeah. One more slide of results, and then that's it. So these are now results from neural networks. Bunch of data, so same methods as before on the top. Also now going to have FedLab-Func, and then on the y-axis of the table, down the rows, you have 4 different data sets, 4 different benchmarks. MNIST with a heterogeneous split, fashion MNIST with a homogeneous split, fashion MNIST with a heterogeneous split. I didn't include MNIST with a homogeneous split because everything is basically the same. Everything performs very well. And then CFAR10 with a heterogeneous split. We actually just used 10% of fashion MNIST because that sort of fashion MNIST, like MNIST, is relatively simple, so reducing the amount of data makes things more interesting. Otherwise, everything again looks very similar. And the heterogeneity, well, how do we sample this heterogeneity? Do the same thing that previous works do, which is sort of sample from Dirichlet distributions to say exactly how many data points should be in each client and how many data points from each class should be in each client. So you get something like, there are 10 clients in total. Each client, of course, has up to 10 classes from each of these data sets. And like half of the data in each client is from 2 classes, on average. You sort of sample this. Again, never mind about all of the sort of sheer number of numbers, but the point is, again, FedLab and FedLab-DIN perform very similarly always. And then, so I'll just give it a second, so like MNIST, fashion MNIST, heterogeneous, and then CFAR10. And then when looking at FedLab-Cov and FedLab-Func, these generally, FedLab-Cov especially, and usually FedLab-Func perform better, or at least as well as the previous methods. Slight note on FedLab-Func here, so the way that I set it up in these, or we set it up in these experiments is to send 1 data point per class per client from each client to the global server, which strictly speaking breaks this federated learning assumption of requirement of not sending any data. I think it's a very slight break because you're usually only sending up to 10 points in total ever from each client. But it'd be interesting to compare these methods, like FedLab-Func, but applied with a federated distillation kind of method with this unlabeled data set. Okay, so to summarize, we derived this method FedLap by taking an approximation to Bayesian federated learning. Saw that it was closely related to FedADMM and FedDin, these previous methods that perform very well, but with a few improvements and insights gained. So firstly, we're targeting a global loss with a weight decay, so better global loss in many cases. And there is no local weight decay requirement as there was in FedDin. We can improve our method by improving the posterior approximation, and showed that in 2 ways with the covariance matrix and function space. And sort of interestingly, this FedLap form was derived similarly to memory-based function space continual learning methods. Future work, be good to look at links between FedLap func and federated distillation. The two are fairly closely related, even though I didn't get into detail, so that'll be good to look at. FedDin and previous methods go into detail of convergence rates. They sort of make some assumptions on the structure of the local loss and so on to say to find a convergence rate. You haven't done that with FedLap, so it'd be interesting to look at that and probably make the same assumptions as previous work and probably reach similar things. And lastly, because all of this was derived with like a Bayesian framework in mind, we can definitely apply this to continual federated learning, where we use like Bayesian continual learning ideas within each local client, so that'd be a good thing to try out. All right, that's it. Acknowledge. Any questions?
Thanks for the talk. I have like one direct question, maybe it's like implicitly going on the thing I mentioned here. So if I just remember your table on the images, image data sets, all the heterogeneous values, they were very, very close to each other, right? So I am like there exist methods in like federated learning that work more on like parameter decomposition things. So like if you went heterogeneous, like you don't need to do continual learning. You just say that each client has like one client has a 1, the other client has a 2, the other client has a 3, and so on. Right? It's like I assume your thing probably failed, or is that wrong? Like I'm not sure that this department means that would be able to handle that somehow.
I didn't try that, so that's a very heterogeneous setup. I haven't tried it, but I don't think it would fail, just convergence will be slower. So we did that with PVI, the previous paper, which is with the KL divergence and everything, that exact setup, and it does learn, it's just slower to learn. So I expect this would also do that.
Yeah, that would be interesting.
Yeah, so these experiments, so it's a very specific heterogeneity level, and one can try different levels. And the more heterogeneous it gets, the more difficult it is to learn, of course. Yes.
Hello. So can I ask you a series of naive questions?
Yes.
Okay, so this is the perfect slide for that. So I'm trying to understand what happened on the heavy list.
Yeah.
So in this, like 60,000 samples.
Yeah.
Each round, how many clients do you have here?
10 clients. So there'll be
clients, right?
Yeah.
And in one round, what happens? Like each client gets a subset of image data.
Oh, sorry. So the data is fixed within each client. So we first fix the data split among the clients by
so
doing this.
6,000 per client.
Well, that would be the homogeneous case. In the heterogeneous case, it varies a lot more. I think some have. I have to check.
Some gets more than the others.
Some have like up to 5 to 10 times more than, like the biggest has 5 to 10 times more than the smallest.
Total
But
60.
overall 60K, yeah.
60. Okay, so they have, say client 1 has 10K. So each round, each time is going over all 10K.
Yeah.
Next time again 10K.
Yeah.
So if I'm thinking about the mobile phone use case.
Yeah.
So in my mobile phone, I'm storing 10K samples, and each time I'm going over it again and again. So each combination round, my data set is not changing. I'm wondering whether that's really the use case of federated learning. Is that what we do? It would be more like continual learning, right?
So federated learning, as you described it, I think it is realistic, but continual federated learning is also more realistic. So federated learning, where the data set is fixed, like maybe overnight or something, your data set is fixed, so you can then try and learn a global model based off of everyone's data sets. Continual federated learning is the setup where your local data is changing over time as well. So first you have one K and then another K, like it's continual learning within each client, kind of, and then you want to learn a model over all the data.
Then in this non-continual learning case,
yeah.
I'm wondering whether you still have something like forgetting issue. Each client is actually privy to a small subset and you actually want to learn from the whole data set.
Yeah.
Is there an issue like that you're aware of?
There is. So yeah, one can view it exactly like forgetting, like in continual learning. This setup where because you only have access to your own data and not everyone else's data, you might start making mistakes. Or you can overfit. Okay. Here's that one. So yeah, you can view it like forgetting, but the difference here is that you can communicate multiple times. So you might forget in some way, but the next round of communication, maybe you try and fix that.
And in one communication round, you do multiple passes in the
yes.
time. You do, how many is that?
It was a hyperparameter. Like so with FedLap at least, and FedDin, I think the more the better, basically. So sort of just capped it at some point, and then
one person you split it into mini batches.
Yeah.
You will also do that, right?
Yeah.
Probably the last question. And maybe some version of federated learning will also not communicate through pressure but through gradients.
Yes.
Right.
So they don't communicate gradients; they communicate changes. The change overall. Wait, okay, never mind. I'm not going to get this quickly. They communicate the change in parameters. So if you took just one gradient step, then that would be equal to the gradient. But if you took multiple gradient steps, then it's like the sum of all the gradient steps so far as the thing that you communicate. And mathematically, that ends up being the same as what I wrote. But in practice, it's nicer to send deltas or changes as opposed to the actual parameter, because that means if, like in this asynchronous setup where clients might drop out or something, then things work out nicer.
So even though mathematically you wrote this way, in practice you probably send the changes.
Yeah.
Just a really quick follow-up to this. Did you just say like the more updates the better? Like if I think of federated averaging, like usually there's a trade-off, right? Like if you do too many local updates, like you kind of diverge, you get into like async kind of stuff.
Yeah.
Can you explain why this is different for your thing? Like why the intuition comes from the more updates are better?
Yes. So the intuition is because we're targeting the local loss that we have. This local loss here targets the right thing, and by the right thing I mean as a solution, the WK that you learn is sort of the WG star. So the closer you get to it, the better.
Okay, so in the sense of that, even one more hyperparameter in the sense of that, right? Because usually in Fed averaging, you would have you'd have to very carefully decide on number of communication rounds versus number of local updates in between.
Compared to federated averaging, yes, removed another one. But compared to like Fed ADMM, which also has this property, then that's not removing an additional hyperparameter. Yeah.
It's all written a little bit, like right now it seems inaccessible, but over the years you will see that it's actually really fundamentally based in construct. You could call it like reconstructing the gradient or sending the gradient, but in the end it's like sending the natural gradients, matching the natural gradients. Right? So it's and then you can rewrite it in different ways. You could sometimes represent with the actual gradient, sometimes with parameters, sometimes by having the delta replaced with the covariance matrix. But if you only look into the ADMM view, you may miss all of this. You know, that somehow these deltas represent uncertainty about the parameters. That these v that you write relates to gradient somehow, right? So there's all these different components, and I think how we really going to solve this is by thinking for which problem, what's the best representation to find these things.
I have a question about the Bayesian approximation at the beginning, when you're mentioning the analogies with expectation propagation, right?
Are you from the UK?
Yeah, it's very.
No, I was just wondering because there is the client's contributions and the QK, which I guess is what the clients use to predict on their own machines, right? Does that make sense?
Yeah. So at a station point of this entire algorithm, QK is equal to QG. So yeah.
Okay, because one of the things in EP is that they only normalize what would be Q of G energies, right? So if you get TKs that are actually not solutions, but they help with the expressivity of the global thing, but this would not happen in this case, right?
Okay, so with PBI, so this is old work, that can happen, and that's why having a row, a damping factor can help. If your damping factor is equal to 1, then sometimes it can be possible to get not, like negative covariance or something, which is obviously same in EP that happens. But if you set row correctly, then that doesn't happen. Again, same in EP.
If you use natural gradient, it will never happen. There's a talk tomorrow given by Thomas on this.
Well, actually, so now I'm going to ask another thing. I would assume that would be like a feature, not a bug. At least in EP.
Like that it goes negative?
Yeah.
Oh, no. No.
Because one thing is the site, another thing is the distribution.
Yes, but somehow things are additive, right? When you add things, they should not go negative. Right? So basically I'm saying that eventually, of course T is not a distribution. It could go either way. But the whole distribution should remain a valid distribution. That's what EP doesn't ensure. Right? EP doesn't optimize this objective. So I don't know why the hell we're talking about EP. Right? Sorry, it's been 20 years, right? It's been 20 years of my life just pushing this thing. So I have to say this. Let's move on. Let's think about objectives that are actually written here, right? We're still stuck in the past. Some places.
Yeah.
You will understand my frustration if you read. Maybe Zane's going to say something.
I'm not going to say about EP, okay? Okay, so your method needs to communicate both the mean, well, let's say the two natural parameters, right?
Yep.
So does that mean, okay, if you don't do anything about whatever adding noise or clipping the gradient, then it will be more susceptible in terms of EP to local data?
So the one that requires sending two natural parameters is the covariance version, right? The non-covariance version doesn't send two parameters, to be clear, just sends one. This version only sends the V case, there's no additional covariance or additional natural parameter. But yes, so with FedLabCov, I can imagine that there is more privacy loss because you're sending more information. I don't know, I don't think anyone's actually proven this with Bayesian methods or something versus not, like with the Bayesian neural network. But yeah, I imagine that is the case.
Okay, then how are you going to make it private?
Oh, you can, okay, so if you want to make it differentially private, you can add noise in sort of clever ways. Or you can come up with a bunch of ways to make it private. I can get into details if you want. Didn't do that in this work and sort of older stuff. So differential privacy one option is to just make this optimization problem differentially private by adding noise to the gradients, right? Another option is to add noise to the parameters that you're sending. So when you send the two natural parameters, you send them plus some noise.
And there's actually, we actually do have a TMNL paper on this with PVI, differentially private PVI, if you're interested in the various options you have.
Okay, so in the interest of time, let's thank the speaker.
So I introduced to you Rio Yokota, who is a professor at the Global Scientific Information and Computing Center at the Tokyo Institute of Technology. His research interests lie at the interaction of high-performance computing, linear algebra, and machine learning. He's the developer of numerous library for fast multiple methods, actual low-ranked algorithms, and information matrices in deep learning. The scale to the full system of the largest supercomputers today. So, please.
Okay, thank you, Kenichi, for the introduction. So I work with MT on the CREST project. So my field is high performance computing. I'm not a statistician or a mathematician, so I'll try my best to entertain you with what I've been doing. So I have 3 parts for my talk today. First, I'll give an introduction to these matrices and deep neural networks, how they work in the actual implementation in PyTorch. And then I'll give a overview of work from 2 of my students. One is Zongbai, who is here, and Satoki Ishikawa, who should be joining online. So yeah, let's start. So in deep learning, you have a bunch of different matrices that appear in different applications. So H is the Hessian, F is the Fisher, C is covariance, and they not just appear in preconditioning optimizers, which a lot of the focus is on, but also they can be used to predict something called the critical batch size, which tells you how large your batch size can be for it to before it starts to lose generalizability. Also, you can use it to predict hyperparameters, and I think also the most common use case nowadays is to use it inside generalization metrics. And so things like the Takeuchi information criteria include these matrices, the Hessian matrix and the covariance matrix. So the point I want to make here is, being able to compute these matrices is useful beyond just optimizers. Okay, so let's define the variables we'll use today. So let's say you have a 2-layer fully connected neural network. The output is a distribution like this, and you have labels, one hot vector. Let's call this Q, and the output P. And the distinction between these 2 things is important because, let's say you input a different image, you have something like this. Okay, so the negative log likelihood per class per data sample is shown with the small l, and the sum of this over all the data and all the classes, or actually all the data in the batch and all the classes is large L. This is the overall loss, which is what you actually try to optimize for. With these notations, you can express the Hessian matrix, which is used in Newton's method like this, the generalized Gauss-Newton method like this. By the way, Z is the softmax, the input to the softmax, or something people call pre-softmax. And the Fisher can be expressed like this, and preconditioning with the Fisher information matrix gives you the natural gradient descent. And some people approximate the Fisher using this uncentered covariance and call it empirical Fisher, but this is not actually the Fisher if you look at this difference here. So with these definitions, let's go into how these things are actually computed in practice in PyTorch. So just to clarify, these forward operations are represented in different colors, and then the back propagation, each of these layers are expressed in these different colors, okay? And you use the chain rule to compute the gradient with respect to here W0 from the first layer and W1 from the second layer. And actually, this is, as you can see here, this is a Kronecker product. It's actually, the Kronecker product is being computed inside PyTorch during the backprop. This is between the activation and the error signal. Same thing for the second layer, right? So if you, in index notations, you have different indices for the activation and the error signal. Okay, and now with this notation, let's look at what happens to the Fisher matrix. So this is a sum over data in class, but if you look at just the two layers, you can express these in like a block form. You have the first block for the first layer, second block for the second layer, and you are actually multiplying these 2 by 2 block matrices, which gives you this kind of shape. Okay, and then if you look at these cross terms here, you can express this as a product between the red, blue, yellow, and green, right? And then this turns into, you can of course swap the order because these things commute. And this is actually a Kronecker product, right? So if you want to code this in PyTorch, you need to use something called the forward hook, and the in data gives you these x's, and the out grads of a backward hook gives you these error signals. And this is per sample, and you can compute these per sample, and later sum for the whole batch, and that's how it's usually done inside PyTorch. So if you think about this, then you can see that for most neural networks which have linear layers, so fully connected layers are linear, convolutional layers are linear, self-attention is linear. The nonlinearity happens in the ReLU, but in this case, also the second derivative is 0, right? Because it's a piecewise monotonic, linear function. So all these things go to 0 in the end, right? Like for this example, except for the last layer where there's a softmax cross entropy, right? So the second derivative of the softmax cross entropy is what remains, and that gives you, by definition, the generalized Gauss-Newton matrix. So originally, you wanted to compute the Hessian matrix, but you can easily see that that's equivalent here, right? And then how this is actually computed is through backprop, but we can view the back propagation as a Jacobian vector product between the Jacobian matrix of the pre-softmax part and the final vector of the softmax cross entropy. And then if you want to compute the Gauss-Newton matrix, you just need to, instead of the normal backprop, which gives you the gradient, you just need to compute matrix, Jacobian matrix product. And that is how you can implement a generalized Gauss-Newton matrix, but also computing this is still expensive, right? So you want to further approximate this. By the way, this square root of a matrix is just Cholesky factorization because these are symmetric matrices. And then if you look at the Gauss-Newton matrix versus the Fisher matrix, there's this difference here, right, shown in the green. That part of, what was the second derivative of the softmax cross entropy becomes, for the Fisher matrix, it's computed with this outer product between the gradient with respect to z, right? So if these two green things are equivalent, if we can show that these two things are equivalent, we can show that the generalized Gauss-Newton matrix and Fisher matrix are equal. So yeah, softmax cross entropy is defined like this. So I'm going to use index notation just because it's easier to manipulate these tensors. And so different indices indicate different dimensions in the tensor. So you have a matrix for the Jacobian with respect to z, and then the Jacobian of the softmax cross entropy can be expressed like this. It becomes very simple. And then, this just define the negative log likelihood per class per data sample. We use index k for that. And now, if we look at the first green part of the Gauss-Newton matrix, you can actually see that very easily, because if you use this equation here, Jacobian of the softmax cross entropy, it's trivial to show that taking the z derivative with respect to I gives you this kind of form. Okay, now let's see if that green part of the Fisher matrix can actually be turned into the same thing as this. And so we go over, if you write down this tensor in this form, here the Einstein summation for k is explicit, be shown as a summation mark. And then with a little bit of manipulation, you show that it actually turns into this thing, right? So just because this thing has a summation over the class doesn't mean, they're not equal things. You can actually show that these are equal things. Okay, so now that we know that these things are equivalent, then let's see how these things are currently approximated in different studies. So almost everyone uses layer-wise block diagonalization, right? And then they further approximate these blocks using different methods. Also, the summation over the class, if you have ImageNet with 1,000 classes, you don't want this summation over 1,000 classes. You want to use more Monte Carlo sampling for that, and it's typical for a lot of these methods to use sampling. Well, the good ones use sampling. The really bad ones just use the Q distribution instead of the P, like people who use empirical Fisher. K-fact does not necessarily require an empirical Fisher. Some people use Monte Carlo sampling for this formulation, but this equation here is using the empirical Fisher version, which gives you this kind of form. Okay, so in the previous slide, I showed that you can decompose the gradient into a Kronecker product between the activation and error signal, and then you swap the order between the outer product and Kronecker product, which gives you this third equation, the second equation from the bottom. And then the approximation actually happens afterwards. So this is the approximation that K-fact does. It first takes the summation over the batch before it actually computes the Kronecker product. And you can also extend this to Gauss-Newton matrices. So instead of having the outer product there, you can have like this Gauss-Newton matrix of the final layer, and you can take the Kronecker product of this. And actually, you can start from the final layer and then do a recursive approximation to do the full Gauss-Newton approximation for all layers. So that technique is called K-FRA. And then more recently, this second order method called shampoo has been quite popular. And if you want to see the difference between K-fact and shampoo in a nutshell, it's basically, it can be shown as like this. So the difference is in the preconditioning matrices. So you can actually turn, because there's this rule for a Kronecker product between two matrices multiplied by a vectorized matrix, X, it actually turns into a triple or double matrix product, A times X and X times B, right? So these are all matrices, right? And vec means reshaping the matrix into a vector form. So if you originally, these weights and gradients are in matrix form, right? So if you have like a fully connected layer that looks like this, it turns into a 3x5 dense matrix. And if you stretch it out, it turns into a length 15 vector. So that's what's shown here. And according to this form, you can express this Fisher inverse as a 15 by 15 matrix. But what's actually computed is not this, right? You don't actually do this inside PyTorch. What's actually computed is using this equivalence, you actually take this preconditioning matrix A inverse and B inverse, and you multiply it to the matrix form of the gradient. Okay, and because this is a 5 by 5, you can multiply it to the 5 side, and 3 by 3 gets multiplied to the 3. Right, the dimensions are matching. And it's important because you can see very easily that this turns into a 5 by 5, right? And B, this is because X is a like 3 vector for this kind of activation. This turns into a 3 by 3. Now, what Shampoo does is instead of separating this activation and error signal like KFAC does, it doesn't separate those two things. It just takes this gradient in matrix form, it's a 5 by 3 matrix, and you use the gradient transpose to get the 5 by 5 thing, and you use the gradient transpose gradient to get the 3 by 3 thing. But this means you're doing the gradient squared, so you need to sort of take the square root. And also, they use a preconditioning with a square root inverse, right? So instead of a square root, this becomes a power of 1/4 in Shampoo. If this were using the same kind of F inverse as KFAC, then this would become a square root, like a 1/2 instead of a 1/4. But there's a second difference that makes this into a 1/4. So I think you sort of get a clear picture of what Shampoo is doing and how it's different from KFAC. And so I'll switch to the second part. Okay, so this second part of the talk is going to be about Shampoo, which I just introduced. And so, yeah, this is becoming quite a popular method. There's actually an extension of Shampoo nowadays that the authors claim to be an even better optimizer, but I'll stick to the original Shampoo for these explanations. So you can show that it practically performs good on training transformers, right? So like it can be used for training these big large language models, and you get even a bigger speed up if you use a distributed version of this. So this MLPerf, which is operated by ML Commons, actually benchmarks a lot of different optimizers and sort of compute for this speed. And they get very good benchmark scores on this. Not that this is like a ultimate target for anyone, but just showing you that these second order optimizers are still evolving. And so yeah, this is I showed the shape of these two matrices and that they're using this 1/4 inverse to precondition. And so what's actually being computed is these things. So you form L and R, the left and right preconditioner, using GGG and GGG. And then you need to take the 1 minus 1/4 power, right? And so computing that cannot be done through like normal matrix factorization or inverses, because if it were 1/2, you can use like Cholesky, and if it was an inverse, you can just invert the matrix. But this minus 1/4 power is a little bit not so straightforward to compute. But they actually compute this using a method I'll describe later. But anyway, so what this turns into inside, if you look at the implementation inside PyTorch again, this is again a more implementation related issue that I'm discussing here. So it turns into a lot of small matrix multiplications. So each of these tiles are matrices, and a naive implementation just computes each matrix multiplication at a time, right? So it sort of serializes these things. But there is actually something called batch matrix multiplication on modern GPUs, and taking advantage of this gives you a lot better performance. And the original implementation of Shampoo does not do this. So we were working on how to batch them. Another thing is you can reduce the precision, right? So instead of FP32, there's this different type called TF TensorFloat 32, which you can compute much faster on something called a tensor core that you have inside modern GPUs. So a lot of our work also involves this conversion into lower precision and using tensor cores. And so how much speed up do we actually get using this? So this is the model size, number of parameters, 8 million to 125 million. And for the 8 million case, the original PyTorch implementation is very, very slow. So normalized with, according to the original speed, which is shown as 1x, the naive iterative implementation of this Shampoo preconditioner is very slow. So you can get a lot of speed up, like 60 times, or even 80 times using this red method. For larger models, the original implementation is already quite efficient, but still we get like 3.7x speed up by doing what I just described in the previous slides. So then there's still room for improvement regarding the implementation of these matrices. And regarding the low precision, so you can actually start out with high precision, like, well, this isn't that high, it's single precision, FP32, but then switch to a slightly lower precision called TF32, and use tensor cores. So here, if you switch to TF32, then the TF32 iterations are much faster, but you get an error plateau, and then you switch back to FP32, and then it converges. Right? So you can use the fast TF32 on tensor cores until it sort of plateaus, and then the rest you can do with the slow FP32. So this switching seems to be a good technique also. And you can combine this with distributed parallelization. So 0 is it's actually the original name, I think, comes from zero redundancy optimizer. It's basically a way to train on distributed, like many GPUs. So combining with 0 and the Shampoo optimizer, you can actually, so this thing shown here in percentage is the actual overhead of having to do the preconditioning, right? Atom W doesn't have this overhead, but Shampoo does. And originally it's taking like 64%. But you can actually reduce this as you scale up to, just even 4 GPUs, which many people have. You can already reduce this overhead of computing all these matrices to 17%. So if you go further, like this can be further reduced, and then you don't need to worry too much about computing these matrices. So yeah, you can reduce the overhead. So this is the key result here. And you can reduce it to 70%, even on just 4 GPUs. And you can use techniques like blocking and different precisions to further accelerate the training. So if you combine all these things, then yeah, Shampoo doesn't have such a big overhead. So that's the second part of the talk. Okay, now moving on. Yeah, switching gears. So this third part of today's talk is going to be very different. Well, it's somewhat related in the sense that it's still about second order optimization, but it discusses a technique called mu p, mu parameterization. So it's about, well, I'll mention what it's about shortly. So it's a stable parameterization that induces feature learning. I'll explain what this means. So the motivation here is we can't tune hyperparameters when the models become too large, right? So, for example, if you're training like, a 100 billion parameter model, you can't run it more than once, right? It's just, you're using like thousands of GPUs for many months, and you can't really do hyperparameter tuning in that setting. So, in that sense, you want to tune your hyperparameters using a small model, but you still want this to somehow transfer to large models. So what is the relation between the hyperparameters for the small model versus the hyperparameters for the large model? And by hyperparameters, I'm talking about things like learning rate, or in the case of second order methods, the damping. And so this mu-p study originally discusses how these hyperparameters scale with the width of the layers. So say that you have a given network, you make each layer like exponentially wider and wider, and then what happens to the optimal learning rate? So you can see the optimal learning rate by looking at the test accuracy. So where it's peaking is obviously where the optimal learning rate is. This thing that says SP is the standard parameterization, or basically the normal setting. Of course, the peak learning, the part where the learning rate peaks, or the test accuracy peaks, according to the learning rate, differs, right? For different widths, of course, you need to change the learning rate to get maximum test accuracy. But with the right parameterization, with mu-p, is peaking at the same point, meaning you don't need to change your learning rate when your model gets bigger. And so this has, as you can imagine, significant advantages, right? You no longer need to go around tuning the hyperparameter, especially the learning rate. But there's a deeper question here. So, in what sense is this related to the feature learning? So here we contrast feature learning from like kernel learning, in the NTK sense or NNGP sense, where the model is, so if the initialization weight scale is large, then the weights converge closer to their initial values, right? This is sort of in the lazy regime, as opposed to the feature learning regime, right? And so this is typically what happens when your layers get wider, right? It sort of asymptotically goes to this regime. However, if your initialization weight scale is small, which is typical in deep learning, then it goes to this feature learning regime where to reduce the training loss, the weights need to be moved significantly, and a rich representation is obtained during that process, right? For Bayesians, you may think about this from the initial values being your prior distribution, and how important are those things, right? This one tends to put a lot of weight on the initial values. It doesn't go too far away from the initial values, but the feature learning moves very far from the initial values, so it's not respecting the initial distribution of the weights at all. I'm talking about the weights here, okay? And then, so to understand mu parameterization, so this is something called the ABC parameterization, which you can see for these constants, A, B, and C. So M is the width of your layer, okay? And when that scales up, what is the exponent, the right exponent to apply here for the weight scale, or the weight initialization scale, or the learning rate, right? And if you have the right parameterization here, if A and B and C are the right values, then you don't need to change the learning rate when your width gets larger. You don't need to change the initialization scale when the weights get larger. So all these hyperparameter optimization parameters that usually appear and that you need to tune for, you don't need to tune if you know the parameter scaling law. Okay, so this is called ABC parameterization, right? We have A, B, and C, and in standard parameterization, the accuracy, if you change the width again, the accuracy changes. Oh, sorry, I thought there was something here, but apparently it's missing. So you need to parameterize, you need the right A, B, and C, right? So you want to find the right A, B, and C. So mu p is an ABC parameterization that satisfies these characteristics. Okay, so what is this? So this is the big theta bound, right? It's bounding for both sides. The upper and lower bound to a constant, right? Big theta is order 1. And so the pre-activation vector h for each layer, the layer is shown in small l, this difference between the initial value and the actual final value at time t, or iteration t, is bounded, right? It's upper and lower bounded. And then also the weight difference, and also this delta h times the weight, and this large L means the last layer, is bounded, right? It's a constant. So with these, the ABC parameterization, if it satisfies these conditions, then it satisfies the mu parameterization. So yeah, this comes from, maybe I should have mentioned this in the beginning. This is published in a paper, it's on arXiv, and by my student Satoki Ishikawa, who I don't see online, but he should be. And so anyway, so mu p, although it's nice, you don't need to tune hyperparameters, but it was only done for first order methods, and also, adaptive, first order methods like Atom and SGD. But so the paper that was just described, it's on arXiv, tries to do this for second order, right? So we look at, I describe what K-fact is and what shampoo is and the differences. Here, we explicitly show this damping term, right? We actually add something to the diagonal. And also, it becomes important, this rho parameter is a new hyperparameter. Can we use this mu p to actually automatically have this parameter scale to larger widths, right? So that we don't need to tune this very nasty hyperparameter. So for those of you who have done K-fact or shampoo, you know that this rho value is very important, right? Your convergence is very sensitive to this rho value. And of course, this has, from a Bayesian perspective, this has deeper reasons. But here, we're just looking at this in terms of the sort of asymptotic behavior when you make the neural nets wider. So it's sort of looking at it from that perspective. So what happens if your width goes to infinity, right? And somewhere along the way, eventually, if it goes all the way to infinity, you get the lazy regime, you get MTK, right? But somewhere along the way, right, it doesn't automatically immediately go to infinity. There's like a finitesimal region where the width is large, and what is the asymptotic behavior during that trend when the width keeps increasing? So, the question here, does default parameterization work with models with infinitely large widths for second order methods? So I'll show later that there's something different between second order and first order methods when you look at the change in, for example, the learning rate scaling. when the width becomes larger. But here, the important point is that the answer is no, right? You need something like this mu p. You need that A, B, and C parameter to be the right scales. And this means you want to initialize the head is like the last layer, with smaller scales, and the learning rate should be scaled per layer. Okay, so this is your typical second order method. Here I'm showing the Gauss-Newton matrix with the damping term, rho, and you have this E, which can be E or like 1 or 1/2. So how does this mu parameterization benefit second order optimization? Can it justify the hyperparameters like damping and learning rate? So that's the objective. So in conclusion, in the ABC parameterization, right, the B is the scaling of the initial weights distribution, and C is the scaling of the learning rate. So what you want to do is have 0 for layer 1, and between 1 and the last layer, you want 1/2, and then 1 for the last layer. For the learning rate, you want to scale this according to the width of each layer. The first layer scales like E minus 1, in between it's 0, and the last one is 1 minus E. Right? And so E is 0 for SGB, which means this becomes -1, 0, and 1. Right? And for Gauss-Newton and K-FAC, the E is 1, meaning that this is 0, 0, and then, they're all 0, yeah. So for shampoo, it's a little bit different, mainly because it's preconditioning with that 1/2 instead of the inverse. You get E equals 1/2. And there's this difference between these different methods, between SGD and these two types of second order methods, and also shampoo is even different from that. And also, I mentioned about the damping term being a huge pain, right? So we found the type of parameterization that makes this width invariant. So D, if you set it like this, except for the first layer, you set to -1 and the first layer to 0. Also, last layer for DB. So DA and DB are the damping terms for the exponent of the width scaling on the damping term with respect to matrix A and matrix D. So this is matrix A damping term, matrix D damping term. And then for shampoo, you have, instead of A and B, you have the left and right preconditioners, but you can still think of this as both A and B, because it's the same in the case of shampoo. You need these scalings for the D in shampoo. So, an interesting thing, though, here, I mentioned that SGD with standard parameterization, like the default SGD without any kind of UP, has a peak at different learning rates for the different widths, right? You change the width, you need to change the learning rate for it to give you the best test accuracy. If you use SGD with μp, that matches. However, if you look at K-FAC without any μp, like with the standard parameterization, it's actually not that bad, right? So the optimal learning rate doesn't need to be tuned so much when the width increases, and if you use μp, yeah, it's still, the optimal learning rate is still at the same place. So for K-FAC, you don't really need to use this to have the optimal learning rate. However, for the damping term, you have the heuristics one is what people usually use. You see this drop off at the very left side, and this shifts, right? The optimal damping rate changes with the width. And if you rescale this with mu p, with the right scaling, then this cliff completely matches, which means you can keep using the same damping rate, damping coefficient across different widths. And so when you do all these experiments, you wonder, is this generalizable across different models? We tested VGG, resonant 18 and 50, and for all of them, using the mu p version of KFAC and shampoo actually gives you an advantage, right? So compared to like the standard parameterization, the mu parameterization gives you better accuracy. Regardless of the model architecture, so this is sort of generalizable across all architectures. So what is the conclusion here, right? So Gauss-Newton, KFAC, and shampoo can be unified in terms of mu p since they have the same mu parameterization, except for that 1/2 thing. And then, however, optimizers with diagonal approximation, like Adam or Ivan, the mu p behavior is a little bit different from the ones that actually compute matrices, like Gauss-Newton and KFAC. So for the viewpoint of infinite width models or like extremely wide models, their dynamics might differ when you make them wider. Also, Gauss-Newton or KFAC automatically adjusts the learning rate scale for the width. You saw that the original KFAC without mu p already had matching learning rates when you change the width, right? But instead, it's more sensitive to the initial weight scale. And these methods, people say they tend to overfit. This might be related to that because they're very sensitive to the initial weight scale. And this is not invariant. So you need to go back, really look at how wide your networks are, and see if you're using the right initial weight. Okay, and for continual learning or fine-tuning, like continuing from some pre-trained model, then basically this is in the realm of not updating the weights so much, right? It's the thing I described earlier, like the weights converge close to their initial values, and it's not a toy problem. This is actually happening in like the real case of large models. When you fine-tune or continually train them, you are actually working in this regime, right? The lazy regime. And this is when you're pre-training, the initialization weight scale, you start small and then you train from scratch. In this case, you're in the feature learning regime. Okay, so I think I showed this exact same slide earlier. And so, in terms of continual learning, there's a paper, Wide Neural Networks for Catastrophically. And so, this is sort of related as well. Like wider models don't move far from their initial value because they're in the MTK, the lazy regime. And that could happen when you're fine-tuning or in continual learning. Also, these are the results from that paper. And so, because this is a Bayes-Duality Workshop, what is this thing? Oh, is it on your side? Yeah, it's not on my screen. Okay. So this is a plug for, So I mentioned about mu p in the third part of my talk, right? And so how can you interpret this? Maybe there's a better way to interpret this than just having the right scaling or the scaling exponent for the width. Maybe there's a better explanation from the Bayesian perspective. And the essence of feature learning is that if the initial weights are large, then the weights converge near their initial values, and feature learning will not occur, right? So, whether that is a good thing or not is up to discussion. There are these two very separate regimes that we see, and we need to be very conscious about which regime we're dealing with when you discuss these things. It's not always the case that the initial weights are not updated so much. In the feature learning regime, they're updated a lot. And so, yeah, this might have strong theoretical explanations from how important the prior is. So, yeah, since Bayesian learning rule involves second order information, there might be different perspectives looking at this problem from that perspective. I talked about all kinds of matrices in the first part of my talk. What we're doing here is actually trying to take these second order methods, trying to make them hyperparameter invariant, but maybe there's a better way to do this from a Bayes learning rule perspective. Okay, so summary of the third part of my talk is, yeah, basically we identified a parameterization, like a mu p for second order methods, taking it to the infinite width limit, and mu p enables us to transfer the learning rate, and importantly, the damping in second order methods. You can transfer now. You don't need to tune it over and over again. And then, yeah, we achieve higher accuracy experimentally. So, yeah, this seems to work in different cases, and it generalizes across different models. And so we haven't really tested this at very, very large scale. So maybe the next thing to do would be to take this to much larger scale. Okay, so yeah, I think I used up the time for my talk. Thank you very much.
Are there any questions or comments?
Thank you. Thanks a lot for the talk. I really like that last part. So I was wondering, I think like concurrently to this Mirza Day paper, there's one by Rana Session others, which is also some like effective scale I'm forgetting or so. And like, if I understood some of the results correctly, there's also like a sparsity kind of thing going on. So like
sparsity.
Yeah, like very large transformer models are just like inherent, like the representations themselves are inherently more orthogonal. Only like 30% overlap or something. So I was wondering with these like regime kind of results, is this on like an on average result, like they on average, like weights on average move less away, or is it like that some don't move at all and some move more?
That's a very good question. So there is actually a huge difference in the amount of movement between the weights. Some actually do stay close to the initial, even in the feature learning regime, right? And so there's a huge variation in this, but still, on average, like you said, it moves more in the feature learning regime. Yeah, I'm not entirely sure about the sparsity. Like, you would imagine if as your layer gets wider and wider, the sort of information content or like the sparsity, right, it also increases. You'd think so, but I'm not sure how that plays a role in moving from the feature regime to the lazy regime. That's a very interesting thing to think about, though. Yeah, so it's not, you shouldn't think of the layer as like one big block. It consists of these individual weights, and the distribution of that is, I think, a very important thing to look at. But we haven't yet. Yeah, thank you.
Thank you for the talk. I'm interested in the second part of your talk. So, can you explain how did you actually do this speed up of your computation? You mentioned this batch matrix multiplication. So, what exactly is that?
So there is a where's that? So it's just the way PyTorch by default computes these matrices in Shampoo. The way that the original Shampoo implementation is done, it doesn't batch these things. Right? It's just an implementation issue. So it's not that, it was hard or anything, it was just not done in that way. How you actually do this, it's actually very simple. There's a function called batched gem, which is like batched, matrix multiplication. It's available inside the CUDA library that NVIDIA provides. And it's not like we wrote the thing ourselves. We just called that library, which takes in a bunch of small matrices in a batch. And you issue thousands or tens of thousands of these matrix multiplication instructions in one function. You call a library, and it computes the multiplication of these small matrices very, very fast. So it's about how much work you can ship to the GPU in one go. It's like you pack everything into one thing, and the GPU operates much faster if you do this. So that's what's being done here. It's actually, a library we're calling.
So you mean you say this batch gen function in GPU in CUDA? Okay.
Yeah.
Maybe the follow-up question is more general. Okay, so in general, how do you make the low rank matrix computation faster on GPUs? My understanding right now is nowadays this development for GPUs, they prefer big matrix computation, right? So that when you have low rank approximation, then let's say you multiply a long and thin matrix with a small one, and then you do the other thing, that can actually be slower. Although you have, let's say, in theory, flops or the complexity is lower than, let's say, big matrix. So just the general, I have the general question about it.
Right. So you're right that the current GPUs prefer something like this, like big and square. When it becomes very thin like this, it doesn't like it. When it becomes very small like this, it doesn't like it. But the batching is just a way to get around this. So basically, what happens when your matrix gets very thin or very small is that the GPU gets very hungry, right? It doesn't have enough to eat, basically. So what you need to do is, instead of just telling it to do this one thing, or one multiplication of these small things, you tell it to do like tens of thousands of them. And if you don't have that much work to do, if you just have one big low-rank matrix, there's really nothing you can do. But in our case, in this particular shampoo preconditioning, we have many layers with many of these matrices, so we were able to do this because our computation or our application actually required to do this many times, and feeding this in at once was the way we accelerated.
So basically, one way to overcome this is, for example, you do this low rank approximation every layer in your neural network, but then somehow you can batch all the layers together.
Right.
Okay.
Yes.
Hi.
Hello.
I have a couple of questions. First one, probably on the
third. Right. Yep.
Presentation. Yeah. So here you had this interesting statement that if you initialize weights, large values, they converge somewhere nearby, right? So so this statement is conditional on the fact that you're using like locally convergent methods, right? If I use some kind of search method that can jump the weight around, this is not a problem.
Yeah, of course. So this is unique to sort of the stochastic gradient type optimizers that we're using here. And even the second order ones are of that nature. They're just second order stochastic gradient based. Yeah.
Locally convergent.
Yeah.
Right. But I was thinking of like some search method that can jump weights around. For that, it probably not a problem. Okay, so the second question is on the second one. Sorry, you can go back to the second one. Here, I have this confusion about computational complexity and how that relates to computation in GPU, and you're probably the perfect person to answer this. So the shampoo work that you talked about, can we talk in any way about the computational complexity of that method? Because for 125 million parameter model, you showed that it has like 64% overhead on a single GPU. And the 4 GPU part was I'm kind of a bit not so comfortable because it is using more GPUs than Atom, right?
No. It's using this. Yeah, Adam is also using 4. I mean, you see the numbers changing here when you go 1, 2, 4.
Right. So if I have more GPUs, so when Adam is using 4 GPUs, is it getting also speed up compared to using 1 GPU?
Yeah, but basically Adam is using a bigger batch, so the batch size is doubled and then quadrupled when it goes 1, 2, and 4. So it is training faster, right? It's reading in more data because the batch size is bigger. In this case, the batch size is also bigger, but the reason why, even though the local batch size is constant, the global batch size is increasing with the number of GPUs, but the batch size per GPU is kept constant for both. But the reason why, even for that constant batch size, it's getting faster, the reason for that is because the preconditioner matrix computation is actually happening on 4 GPUs instead of 1. Right? This part didn't exist in Atom, so you don't really observe that speed up in Atom, but here, you're actually doing the precondition, the matrix preconditioning part on 1 GPU versus 4 GPUs, and that's why it's getting faster.
Okay, yeah.
And forward and backward are taking the same time. Yeah.
Got it. So thanks for this explanation. So this is good. I'm good with. But back to the original question about computational complexity, right? If I talk about just computational complexity of this optimized shampoo, what would be that?
So I think this slide is easier to explain that. So you can think of this 15 versus 15. This is the number of parameters in this model. So this is order n squared, right? Like 15 times 15. If you do this kind of matrix vector multiplication, the complexity would be like n squared. And inverting n by n matrix takes like n cubed complexity. What happens when you do this Kronecker type factorization? So that's happening both for KFAC and shampoo, except shampoo doesn't look like it's doing a Kronecker factorization, but the end result, the amount of computation is identical, right? You get the same size matrix and you precondition with it. The size of these matrices, if you think about it, because this is a Kronecker factorization, it's actually square root of n, right? You actually decompose it into 2 Kronecker products. Each of their size would be square root of n. So the inverse of a square root of n is like n to the 2/3 power, right? Because there's a square root involved in it. So complexity-wise, these methods theoretically have a time complexity of n to the 2/3.
Into the 2/3.
Yeah, so 1.5.
1.5, so it's still like super linear.
So it's still not order n. So as n gets larger, or as your layer gets wider, you will really see this complexity increase.
So instead of having 125 million parameters, if I had like 12 gigabytes, then those numbers will not remain the same, it will be much larger, right?
Right. So then the interesting question would be, like, when your model gets larger, does it necessarily proportionally get wider and wider, right? If you can just make it deeper instead of making it wider. This is only affected by the width, right? So when you say n, square root of n, it's not actually, n here is like the width of your network, basically. And so that n may not be necessarily the number of parameters in your model, right? You don't need to make your width proportional to the number of parameters, right? You can just make it deeper. And modern neural networks tend to get deeper as they get bigger. So then they're not necessarily getting wider, which means it's not n to the 1.5 per se. Yeah, it's a little bit better.
So, yeah, let's thank Rio again.
Thank you.